What if the secret of life began not with thunder or fire, but with a quiet ripple in a forgotten tide pool, a gentle spark in the darkness that changed everything? Welcome to Sleepster. Tonight, we drift back through unimaginable time to a world without trees, without animals, without sound. A young earth, raw and restless, still sculpting its face beneath volcanic skies, as, somewhere in its waters, something stirred, from lifeless matter to living miracle. This is the story of how it all began. What if Earth was never meant to be alive? What if, long before oceans waved, long before clouds gathered, and long before a single cell dared to divide, this planet was meant only to be silent? We often take life for granted, as if the soil was always meant to grow trees, and the air was always meant to be breathed. But what if it wasn't? What if life was not the plan, but the accident? Let's go back, not 100 years, not 1,000, not even 1,000,000,000. We begin in the before biology. Before biology had a name. Picture the early Earth, not the blue marble we know today, but something wilder, lonelier, and unimaginably still. There were no birds to break the silence, no waves that crashed with rhythm, no trees, no grass, not even bacteria, only minerals, gases, heat, and time moved slowly. The Earth was born from fire, from collisions and molten skies, dust gathered in space, pulled inward by gravity, folding upon itself until it glowed. For millions of years it rained fire. Volcanoes breathed lava into the atmosphere. The air was filled with carbon dioxide, nitrogen, methane. The seas, if they could even be called, that were acidic, boiling, stormy. If you were standing on a shore back then, though, you wouldn't be standing. And there were no shores. You would see lightning slicing through pitch-black skies, hear silence, broken only by wind, smell sulfur and smoke, feel no pulse in the world beneath your feet, no heartbeat, just heat. So how, in a place so violent, so inhospitable, so impossibly empty, did something ever decide to become? That is the mystery we're here to explore together. Not just how life began, but how non-life transformed, how stillness gave way to motion, how something without hunger, desire, or instinct eventually opened its microscopic mouth and said, "I am to understand the origins of life." We must first understand that for the longest time nothing lived, and yet everything was happening. The oceans were forming. Meteorites delivered strange materials, carbon compounds, water ice, maybe even amino acids. Lightning danced across the atmosphere, igniting new molecules. Deep beneath the sea, hydrothermal vents were spewing minerals into darkness. The crust of the Earth was shifting, shaping continents before they had names, and in all this, molecules began to meet. Hydrogen met carbon, nitrogen whispered to oxygen. They collided, they split, they reformed, over and over. For millions of years, they practiced the dance that would one day become chemistry. But still, there was no life, only preparation. Think of a tide pool. Imagine it on the edge of a volcano, warm with heat, filled with minerals. Day after day, the sun bakes it dry. Night after night, it fills again. A perfect cycle of evaporation, concentration, renewal. In this little pond, molecules begin to link together. They form chains. The chains fold. Some break, others survive. Could this be where it began? A single strand of something fragile, barely more than a chemical, but able to copy itself. Not perfectly, never perfectly, but enough to remain. And with each imperfect copy, the chance to adapt, the chance to improve, the chance to evolve. But not yet, because to evolve, something must be alive, and we're still before that. Somewhere in this chemical landscape, a line was crossed, not with a bang, not with a cry, but with a ripple, a change so small it could barely be noticed. A membrane wrapped around a molecule, a wall formed between inside and outside, a separation, a kind of boundary, and in that boundary identity. The first whisper of self. This is not me. That is me, and perhaps that was life's first breath, but even this is still speculation. A possibility, a theory. The truth is we don't know for sure how it began. We can trace elements in ancient rock. We can test reactions in laboratories. We can simulate what early Earth might have looked like. But the moment itself, the leap from non-life to life, remains hidden. Perhaps it always will, but maybe that's part of its magic, because when you look up at the stars and see how many planets remain quiet, lifeless, still you begin to wonder, why here? Why did this rock, spinning silently in the blackness, give rise to breath and thought and feeling? Was it chance? Was it chemistry? Was it something more? We are made of the same elements as the lifeless dust that floats through space. And yet, we ask questions. We wonder. We remember. How did that happen? It didn't begin with consciousness. It didn't begin with intelligence. It began with heat and pressure and time. It began with molecules bumping into each other. It began with failure after failure after failure, until one day, something stayed. And so, before we explore cells and structure, DNA and division, we rest here, in the space between silence and spark. We acknowledge the stillness that came before the storm of biology. We remember that the first chapter of life was written by things that didn't live, and we ask again, not for an answer, but for the wonder. What if Earth was never meant to be alive, but became it anyway? Not through purpose, not through design, but through the slow unfolding of possibility, across eons of silence. And if that is true, then what else even now is becoming something more? Somewhere deep in the ocean, somewhere far beneath the rock, somewhere inside a speck of dust that has yet to remember itself, maybe. Life is still learning how to begin, even now. Before fish swam, before even the simplest microbe drifted through the dark, there was an ocean, without life. No plankton, no coral reefs, no movement beneath the surface but the trembling of heat, the swirling of minerals, and the slow dance of chemistry. It's difficult to imagine water without life, isn't it? We've come to associate the ocean with abundant teeming schools of fish, ancient whales moving through deep blue silence, strange creatures glowing in the abyss. But the first oceans were different. They were still, they were waiting, and they did not yet know what they were waiting for. Let us drift backward, further into the deep. Roughly 4.4 billion years ago, the Earth had cooled just enough for liquid water to exist. Before that, everything was fire and rock, a molten planet, too hot to carry even a single drop. But then, something changed. The surface began to solidify. Steam condensed. Rain fell, and it didn't stop falling for centuries. The first rain may have lasted millions of years, and that endless rain filled the Earth's ancient craters, carving basins, dissolving rock, becoming something new. Over time, those basins became oceans wide, shallow seas that shimmered beneath a blood-red sky. No sunlight pierced the dense atmosphere. No oxygen kissed the waves. The air was thick with methane, ammonia, carbon dioxide, and the seas were not blue, but dark, acidic, warm, perhaps even boiling in places. But they were not empty, even if no life had yet begun. These oceans held ingredients, carbon compounds delivered by meteorites, minerals from volcanic eruptions, metals dissolved from the newborn crust, water endlessly shifting, stirring the planet's chemistry into something it had never been before. You might think of these oceans as a giant mixing bowl, the entire planet, a single, ongoing experiment. There were no cells, but there were molecules, and these molecules drifting, colliding, breaking apart, and forming again began to write a language, not in letters, not in sound, but in structure. They formed chains, chains that folded, chains that looped, chains that began to resemble the basic structures we now call organic. Imagine a single molecule, fragile, simple, incomplete, floating in warm seawater. Around it, hundreds of others, thousands. And within those chaotic waters, reactions sparked. One molecule joined another. Some chains collapsed, some survived, some even began to protect themselves, hiding inside bubbles of fat like membranes. It may sound trivial now, but those bubbles, they were the ancestors of the cell. In this ocean, the first boundaries formed, a wall between inside and outside, The very idea of containment, of keeping certain molecules close while keeping others out, was a turning point. Not yet alive, not yet breathing, but different from the random soup around them. Is that not the first sign of self? And still, the ocean had no eyes to witness it, no brain to comprehend it, no one to mark the moment when lifeless chemistry stepped 1 inch closer to life. This is the tragedy and beauty of the early ocean. Everything was happening, and no one was there to see it. Only the sea itself. The ocean became the first womb.it, carried potential within its folds, cradling molecules that had never existed before in the universe. Not quite dead, not quite alive. Balance between entropy and emergence. Down near the ocean's floor, deep fissures opened hydrothermal vents, spewing heat and minerals into the water. Some scientists believe life began here, at the edges of these black smokers, not in sunlight, but in darkness, not in still water, but in heat and turbulence. Here, temperatures swung wildly. Gradients of heat, acidity, and chemistry changed moment by moment. And amidst this chaos, unique environments formed small, protected niches where reactions could stabilize, where molecules could persist long enough to do something remarkable, copy themselves. Imagine the strangeness of that moment. A molecule, no eyes, no limbs, no intent copies itself. And now there are 2, not because it wanted to, not because it understood, but because physics and chemistry permitted it. That, some believe, was the first echo of reproduction, the first flicker of something that could continue, and once a molecule could copy itself. Even badly, even clumsily, evolution began. Not evolution as we know it, no genes yet, no cells, no inheritance, but variation, trial and error, molecules that copied faster, more accurately, or with greater stability began to accumulate. In the silence of that early sea, the rules of biology were being written by chemistry. This ancient ocean, lifeless in our eyes, was, in fact, the threshold of everything we would one day call alive. And it raises a question, doesn't it? Was the ocean alive even before life? Was the act of holding possibility already a kind of awareness? There's a term used by scientists. Abiogenesis.it refers to the process by which life arises from non-living matter. But maybe life doesn't just arise, maybe it emerges, slowly, reluctantly, with false starts and failures, with countless cycles of forming and dissolving, until, eventually, something endures. And maybe that's what the early ocean was doing. Enduring, shaping, testing, not by will, but by the gentle pull of time, because time is the true architect of life, not DNA, not even water, but time. It took billions of years for the first true cells to form. Billions of years, where no fish swam, no bacteria crawled, no breath was drawn, only an ocean, wide, silent, and full of beginnings that didn't yet know they were beginnings. And still, every one of us carries that ocean inside us. Your blood, salty, mineral-rich, echoes those ancient seas. Your cells, enclosed in membranes, mimic those first chemical bubbles. Your energy flows through channels first carved by primitive life in those hydrothermal vents. You are not separate from that lifeless sea. You are what happened next. So now, when you imagine the ocean, don't picture only coral reefs and whales. Picture the silence that came before them, the chemistry that built the possibility, the stillness that waited long enough to become motion, and the lifeless water that chose somehow to begin remembering, because that's what life is, in the end, a memory written into matter, a pattern that persisted, a ripple that never stopped expanding. And if the ocean could do it once, could it happen again, somewhere else, on another planet, in another deep sea, still waiting? Or is our lifeless ocean now full of life, a miracle so rare, so quiet, so unrepeatable, that we'll never see its kind again? We don't know, but what we do know is that before life began, there was an ocean, an ocean that had no life, but held it anyway. Beneath the silence of the early oceans, beneath the boiling surface, the chaotic skies, and the slow movement of molecules in warm tide pools, there were rocks, And they did not speak. They did not think. They did not breathe. But they may have whispered, not in sound, but in structure, not in language, but in potential, for long before cells began to replicate, and long before membranes formed to separate inside from out. The rocks were already there, ancient, still, and endlessly patient. We often imagine stone as lifeless, cold, passive, something to be stood on, carved into, broken apart, but in the story of life's beginning, the rocks were not the background. They may have been the blueprint. Let's drift back once more to the Hadean Earth over 4 billion years ago. Volcanoes rose from molten seas. Asteroids shattered the surface. The land was unstable, fractured, and constantly reshaping. And yet, beneath this violent exterior, something astonishing was forming. Minerals. The Earth's crust began to cool and crystallize. Silicates, carbonates, metal oxides, all arranging themselves into patterns, lattices, layers. At first, just a few dozen types existed, but as conditions shifted, as pressure deepened and chemistry evolved, hundreds more began to emerge. These minerals weren't just rocks. They were platform-stable surfaces for complex chemistry. In a world without cells, without enzymes, without DNA, molecules had to find a way to stay still long enough to interact. And that's what mineral surfaces offered. Picture this: a tiny molecule, drifting in warm, chaotic seawater, bumps into a crystal surface. Instead of floating away, it sticks, and nearby, another molecule sticks as well. Now, close together, they can react, they can link, they can become something more. This isn't imagination, it's lab-tested possibility. In controlled experiments, scientists have watched clay minerals help simple molecules form longer chains, even chains resembling early RNA. The minerals weren't alive, but they offered a structure, and structure in the beginning may have mattered more than intention. There's a poetic theory that early Earth was like a classroom without a teacher, and the minerals were the desks. Molecules sat down, close to each other, and in the quiet stillness of those surfaces, they began to learn. It's here we meet a beautiful concept: templating. Some minerals have specific shapes, ridges, grooves, repeating angles. These shapes can guide how molecules align. Like puzzle pieces encouraged to fit together, certain reactions become more likely not because of life, but because of geometry. Could it be that the first spark of life didn't come from the sky, but from the ground, from rocks that arranged matter with no awareness? No plan, just the quiet rules of physics unfolding across deep time. And yet, it goes deeper still, because some minerals don't just host reactions. Some catalyze them, that is, they speed them up. Iron-sulfur minerals, for example, found near hydrothermal vents, can donate electrons, allowing molecules to form that otherwise never would. In the dark, pressurized silence of the seafloor, these mineral complexes may have helped build the first organic systems. They didn't invent life, but they created a stage on which life could appear. And maybe that's enough. Imagine this world. Underwater vents spew out clouds of hot, mineral-rich fluid. Those minerals settle onto nearby rocks, forming layers of crystal and metal. Around them, molecules gather. Some break apart, others bind. Over thousands, millions of years, small networks form, molecules that interact in loops, systems that sustain themselves briefly. Not alive, not yet, but trying to persist, trying to hold shape, trying not to fall apart. And what's most humbling, all of this was happening without sight, without sound, without purpose. The rocks weren't guiding with wisdom. The molecules weren't striving with will. It was all just matter, doing what matter does, following possibility, and yet isn't. That the seed of life, the difference between something that simply exists and something that continues. Let's pause here with a question that changes the tone of everything. Can memory exist without a mind? The idea may seem strange, but minerals, in a way, remember. They remember heat and pressure in the way they're shaped. They remember chemistry in the elements they hold. A crystal lattice isn't just beautiful, it's a physical record of the environment in which it formed. And what if these mineral memories weren't just inert records, but active guides? What if the rocks taught the molecules not consciously, but mechanically how to replicate, how to fold, how to stay? You see, life isn't just about being alive. It's about enduring, persisting in form long enough to create again. The first step toward life was not breath, it was stability, and in a world of heat and chaos and constant destruction, rocks were the quiet teachers of stability. Even now, when we peer into ancient geological formations, we see layers not just of stone, but of story. We find banded iron, carbon traces, zircon crystals over 4 billion years old. These stones are not just objects, they are archives. They are witnesses. They carry within them the pure life, the silent era when matter rehearsed existence again and again. And if you listen not with ears, but with wonder, you can still hear their whispers, soft, measured, patient, like this. Try again, link again, fold again, survive, repeat. These aren't just echoes of chemistry. They are the first lullabies of biology. And perhaps the earth was humming to itself all along, not with voice, but with possibility. And now we must ask, if rocks helped life begin here on Earth, could they be doing the same thing somewhere else, on another world, where water meets mineral, where warmth stirs a storm of molecules? Could something similar be happening? Are there oceans right now, cradling lifeless stones? And are those stones once again whispering the shape of something yet to come? Not every planet needs breath, not every world needs eyes, but maybe every world that hopes to become needs rocks, not to live, but to guide life's first fragile steps. Long before cells divided, long before organisms fed, or moved, or sensed the world around them, there was chemistry, simple, blind, unfeeling, and yet, through the rhythms of this early chemistry, something began to change. Something began to become. Let's float quietly into that moment, not a moment in time, but a moment in pattern when the dance of molecules shifted ever so slightly towards something new. This chapter is not about life. It is about the soft, uncertain bridge toward life, the stage before intention, the edge of identity. In the beginning, everything was motion, atoms drifting in more motions, gases swirling in the sky, liquids bubbling around volcanic vents. And inside this motion, elements met. Carbon, nitrogen, hydrogen, oxygen, the scaffolding of biology. Though it didn't yet know it was building anything. When these elements touched, they bonded. When they bonded, they formed molecules. And when molecules encountered others, they formed networks, not minds. Not yet, but relationships. In these early oceans, nothing was alive, but everything was participating. We often think of chemistry as cold, detached, numbers on a chart, equations written in chalk. But here, chemistry wasn't academic. It was creative, chaotic, relentless. Over and over, molecules assembled and fell apart. But some began to persist. They folded into shapes that protected them. They developed slight asymmetries, one side folding more neatly than the other. They began to interact in repeating loops. One molecule triggered another, which triggered another, which returned to the first. These loops weren't alive, but they were no longer random. They were the beginning of systems, and in systems, something remarkable can emerge. Feedback, when part of a network changes and that change influences the rest, a kind of memory forms. Not conscious memory, not thought, but the first hint of information. A system begins to remember what works. It stabilizes. It continues. This is the essence of emergence. When complexity arises from simplicity, when structure appears without a plan. And so, these molecules floating in warm water, clinging to rocks, bathing in sunlight, or curling into shadows weren't trying to become alive. They were simply becoming more stable. And in that quiet stability, the seed of life was planted. One of the most poetic ideas in science is this: life did not begin as life. It began as the ability to remain. That is the chemistry of becoming. It's not about A sudden spark. It's not about one miracle moment. It's about millions of tiny transitions, gradual, forgettable, uncelebrated, until one day a molecule copies itself, not perfectly, not often, but just enough to leave a trace, enough to matter. This self-replicating molecule, perhaps something like early RNA, is often seen as a turning point in the origin of life. It doesn't need enzymes. It doesn't need cells. It just needs to hold a pattern and pass it on. Think about that. A molecule that copies itself is not just chemistry anymore. It is inheritance. And where there is inheritance, there can be evolution. Now, instead of being shaped only by chance, molecules begin to shape each other. Some copies are better than others. Some last longer. Some gather resources. Some fall apart. And through this slow filter of survival, complexity begins to accumulate. Not because life willed it, but because chemistry allowed it. Let's pause here. Close your eyes for a moment and picture it. A microscopic strand of RNA, just a few dozen bases long, floating in a puddle on a young, hot planet. It doesn't think. It doesn't feel, but it carries a pattern, and that pattern makes it possible to build more of itself. It cannot see the sky. It cannot understand the ocean, but it has become part of something new. Something that doesn't just happen, something that continues. Now, imagine that same puddle millions of times across the early Earth, in every warm tide pool, every volcanic vent, every muddy clay basin, each hosting its own little chemical play. Most of these plays end in silence. Most patterns collapse. Most molecules forget, but a few, a rare few, survive long enough to try again, and over eons. Those few become the foundation for everything. Your body this very moment carries echoes of those first molecules, the phosphate backbone of your DNA, the structure of your proteins, the energy your cells use, stored in ATP. All of it evolved from that early chemistry, that unthinking becoming, that slow chemical whisper that said, stay, repeat, continue. We often think of evolution as belonging to biology, to animals and plants, to ecosystems and adaptation. But evolution began in chemistry. In loops, in feedback, in reactions that favored endurance. So we return to our ocean, not teeming with fish, but with potential, not filled with life, but filled with becoming. And here's the quiet truth. You don't need life to begin life. You just need motion and matter and time. You need mistakes, copying errors. You need persistence, patterns that don't collapse. You need space for structure to form. And when all these things come together, something unexpected begins to emerge. Not life, not yet, but a direction, a leaning, a tension, a quiet pull toward organization. Some call it self-assembly. Some call it chemical evolution. Some even call it destiny. But we call it this: becoming. The chemistry of becoming is not a moment in history. It is a process that still moves through us now. Every cell in your body echoes that first puddle. Every protein folds as it once folded in ancient waters. Every heartbeat carries the rhythm of a world that once knew nothing but silence. You are not separate from that chemistry. You are its latest shape, its latest song, its latest possibility. And somewhere, even now, on another world, or in a dark ocean trench, or in a rock pocket warmed by heat, the same chemistry may still be unfolding, still trying, still folding, still becoming. And if so, then life is not rare. It is just very, very quiet at the beginning. How does anything organize itself in a universe ruled by chaos? Entropy, the tendency of all things to move toward disorder, is one of the most fundamental laws of our universe. From the slow cooling of stars to the withering of leaves, entropy governs the flow of time and the collapse of systems. Yet here we are, living beings made of trillions of ordered molecules, built with precision, symmetry, and intention. The contradiction is humbling. If we follow the thread of life's beginning, we must first confront this paradox. How did the earliest hints of biological order ever emerge against the current of chaos? The early Earth was anything but still. Energy pulsed violently through the planet. Lightning strikes, volcanic eruptions, and ultraviolet radiation from a young, unfiltered sun. The surface was a brutal mosaic of raw power. Water boiled and froze in irregular cycles. Chemicals crashed into each other with blind randomness. And yet, through this disarray, something rare began to happen. Patterns started to repeat. Simple molecules began forming more complex structures, not through magic, but through a process we call self-organization, a quiet rebellion against entropy. We see self-organization even today. Snowflakes form intricate symmetrical patterns despite being born in chaotic clouds. Crystals grow into ordered lattices without a blueprint. Soap bubbles arrange into perfect hexagons. These systems find stability by minimizing energy, and in doing so, create order briefly, beautifully. Could similar forces have governed the first spark of life? In primitive Earth's tide pools, hydrothermal vents, and mineral-rich basins, specific conditions may have fostered this organization. For instance, lipid molecules, the same molecules that form modern cell membranes, naturally arrange into bilayer spheres in water. These hollow spheres could protect whatever floated inside, separating inner contents from the harsh outer world, a primitive precursor to the first cell wall. Here, entropy isn't defeated, it's redirected. You can imagine early Earth like a swirling pot of ingredients. The heat isn't just destroying things, it's enabling reactions. The cooling isn't just decay, it allows structures to settle. As energy flows from one place to another, temporary patterns emerge, eddies in the current, not permanent, but long enough to evolve. One theory, called the thermodynamic dissipation theory, proposes that life emerged as a means to accelerate entropy, not resist it. In this view, life is not the opposite of disorder, but a more efficient way for the universe to spread heat, light, and energy across space and time. It's a strange thought that every cell we're made of, may have evolved as an elaborate mechanism to help the cosmos cool down faster, but even that interpretation doesn't diminish the elegance of life. In fact, it deepens the mystery. If all things break down, why did a few things briefly build? Up first, entropy's dilemma is that the same energy that destroys can also create. A volcano that melts mountains can also forge new land. Ultraviolet rays that tear molecules apart can also catalyze new bonds. Destruction is not the end, it is a turning of the page. What we think of as disorder is not the absence of structure, but the overwhelming variety of structures that could form. And sometimes, within that variety, nature stumbles into repetition, a repeating pattern, a stable form, a cycle. That repetition is key. Once a molecule replicates, even imperfectly, it changes the game. Replicators don't fight entropy directly. They use it. They harness the energy in their surroundings to make more of themselves, shifting entropy from their internal order to the world around them. Like little whirlpools in a river, they're local anomalies, organized pockets in an ocean of randomness. This moment, this emergence of replication, is where the boundary between chemistry and biology begins to blur. We aren't quite at life yet, but we're close. The ingredients are assembling themselves into small, resilient patterns. The first whispers of persistence are in the air. Still, the road ahead remains uncertain. How does a replicating molecule gain memory? How does it respond to its environment? How does it grow complex enough to divide, adapt, evolve? We're standing at a ledge. Behind us is the roaring sea of geochemistry and wild energy. Ahead of us, the first shadows of something new, something alive. As we close this chapter, we sit quietly with the contradiction. In a universe that favors collapse, life is a pattern that grows briefly, improbably, and decided not to collapse, at least, not yet. And so, the question remains, open and echoing. Did life begin because the universe made a mistake, or because it was always meant to? Imagine a quiet pool at the edge of a volcanic shoreline. Steam hisses in the distance. The air smells faintly of sulfur, and beneath the surface of the warm water, something astonishing is happening. Molecules, simple, oily, slippery, are dancing. These molecules, called lipids, are unlike the others floating freely in Earth's primordial soup. While most molecules are swept away by waves and heat, lipids begin to behave differently. They gather, they curve, they form tiny spherical shells enclosing a small pocket of water inside. A bubble is born, but not the kind that drifts into the air and pops. These are microscopic containers that could hold the seeds of something much greater. This is the beginning of what scientists call the lipid world hypothesis, the idea that life began, not with genes or proteins, but with the simplest possible boundary, a bubble made of fat. Lipids are amphiphilic. Part of the molecule loves water. The other part hates it. When placed in water, they automatically arrange themselves so the water-loving heads face outward, and the water-fearing tails face inward. It's a natural law of balance, no plan, no design, just chemistry finding a comfortable shape. When many lipids gather, they can form a bilayer, double-sided wall that closes in on itself like a balloon. The result is a vesicle, a sealed pouch, floating freely in the soup of early Earth. And this might have been the first cell-like structure ever formed. Before DNA, before enzymes, before even metabolism, came a membrane, not alive in itself, but protective, selective, and stable enough to carry other molecules inside. That alone is monumental. In a world without boundaries, this was the first inside and outside, the first concept of self inside these lipid vesicles. The stage was set for complex chemistry. Free-floating molecules, perhaps fragments of RNA, simple catalysts, or other active chains, could now interact without being immediately swept away. The walls of the bubble created a localized microenvironment, shielding its contents from dilution or destruction. Suddenly, the chaotic dance of atoms had a theta, a protected space to repeat, react, and evolve, and it didn't end there. These early bubbles could grow by absorbing more lipids from the environment. When they grew too large, some would divide not by intention, but by sheer physical instability. They split, and each half carried a portion of what was inside. Just like that, the earliest model of reproduction began to form: primitive, fragile, but real. No genes, no blueprints, just bubbles, growing, dividing, enclosing molecules. In a world of swirling heat and elemental violence, these simple vesicles might have floated across warm ponds, hydrothermal vents, or salty lagoons. Some may have popped, others absorbed new molecules. A few might have joined with neighboring vesicles, exchanging contents and forming hybrids. This was a form of natural experimentation, played out a billion times across countless pockets of the planet. Now pause and think about this. The very structure that defines modern cells, the cell membrane, is still based on this ancient principle. Our neurons, skin cells, blood cells, all protected by lipid bilayers. Billions of years later, the bubble still stands. But the real question is, did this bubble eventually trap a replicator? Did it one day enclose an RNA strand or a self-catalyzing peptide, something that could copy itself? If so, then that vesicle became more than a container. It became a protocell, a bridge between non-living chemistry and the earliest whisper of biology. Scientists today have recreated such scenarios in the lab by mixing lipids and RNA fragments in warm, mineral-rich water. They've watched vesicles form, grow, and trap strands of genetic material. They've even observed chemical reactions occur inside these bubbles, tiny chemical factories running on primitive rules. What this tells us is simple. The creation of a container, a membrane, may have been the most essential first step toward life. Without walls, no complexity can persist. Without boundaries, there is no identity. Even now, you are a collection of billions of these bubbles, each one keeping your inner world separate from the chaos around you. Each cell, a silent tribute to a time when Earth first learned to draw a line between me and everything else. And perhaps the most elegant part of all, no intelligence was required, no divine touch, just molecules, following the quiet physics of their form. And from that structure, from that stability, from that, the first fragile seed of life. What if the origin of life began not in chaos, but in a quiet place, a shallow pool warmed by sunlight, stirred by rain, kissed by lightning? Charles Darwin once imagined this one little pond, a simple cradle of complexity, where basic molecules swirled, collided, and unknowingly set the first domino in motion. Today, scientists still whisper about this idea not as metaphor, but as molecular possibility in this tranquil pool, perhaps rich with ammonia, methane, phosphates, and carbon dioxide. Life didn't arrive all at once. It brewed slowly over thousands of years. Raindrops delivered chemical visitors. Lightning etched energy into form. Heat from volcanic rocks simmered the solution. Slowly, amino acids began to appear, tiny building blocks of life. Born from non-living parts, we know that under the right conditions, organic molecules can emerge from inorganic chemistry. In 1953, the Miller-Urey experiment electrified a primordial soup in a lab and created amino acids. It was not life, but it was a first step. And the warm little pond, it might have been nature's own lab. Here, the earth was patient. No rush, no deadline. Raindrops carried raw elements from the sky. Volcanoes spilled minerals into the water. Sunlight offered energy. All the right conditions danced within this small basin. And in that slow, quiet dance, chains of molecules formed and reformed, driven not by design, but by probability and time. We can almost see it, a rippling puddle beneath a red, hazy sky. Maybe shadows of early mountain ridges stand in the distance, their slopes bare and volcanic. The surface of the pool bubbles faintly with geothermal warmth, and beneath, molecules meet, bond, drift apart, then meet again. This is not life yet. But it is the rehearsal. It is the act before the awakening. Molecules are learning to hold hands, to protect each other, to replicate. The water is not just a solvent. It is a shelter, a stage, a teacher. Now ask yourself why a pond, and not the ocean. The answer lies in concentration. Oceans dilute fast, but a small pond, it allows ingredients to linger. It allows evaporation to concentrate the soup. It allows cycles wet and dry, hot and cold, light and dark. These changes act like pages turning in a book. Each new condition, flipping the molecular script, cycles matter. During dry spells, molecules might cling tighter, forming chains. During rains, the mix refreshes. And in between, something magical might happen. The first protocells may emerge, tiny bubbles of lipid molecules forming spheres in water. Like primitive membranes, like the idea of a cell. They are not alive. Not yet. But they look alive. They trap molecules inside. They create inside and outside. They establish boundaries. And boundaries, surprisingly, may be where identity begins. In this small pond, there are no eyes to witness, no words to name it. But something fundamental has changed. The earth is no longer only rock and water. Now, it hosts intentionless complexity. Now, it contains entities that protect themselves, even if by accident, one day. One of those fragile spheres might trap a replicating RNA strand. It might stumble upon the ability to copy itself. And with that first replication, a quiet miracle will unfold, the beginning of evolution. But for now, we linger in this warm little pond, this silent basin of possibility. We do not yet name what's forming, but we can feel it in our bones, a sacred slowness, a kind of cellular prayer. Some scientists believe that life may have started elsewhere, deep in hydrothermal vents, or even delivered by comets. But others return, again and again, to Darwin's whispered image, not as nostalgia, but as a reasonable vision, a natural poetry, a theory painted in soft strokes, because in the grand silence of the early earth, this warm little pond may have been enough, enough to begin, enough to remember, enough to change everything. And so, life may have started not with a bang, but with a ripple, a soft bubble, a tiny fold in time's great blanket. Let us pause here. Let the ripple spread. Let the molecules find one another. Because soon, something irreversible will happen. Soon, the first error will become the first memory. Soon, the first copy will make a second. Soon, we will no longer speak of non-life. Now imagine this, a thin film on the surface of a shallow ancient pool. The sky is copper red. The air carries a strange scent, sulfur, salt, and something else. something almost electric, and in the stillness of this world before life, something remarkable has happened. A bubble, tiny, fragile, barely more than a shimmer of molecules clinging together. A vesicle, a sphere, a skin made from lipids, enclosing water, enclosing randomness. Yet within this randomness a pattern. Inside this first bubble lies something new, a molecule that can copy itself. Not perfectly, not with elegance, but copy, nonetheless. And in that copying, the Earth changes forever. This is not simply chemistry anymore. This is the first thread of memory, the first strand that remembers its shape, the first structure that resists time. Inside this simple enclosure, a strange and delicate choreography begins. Some molecules bind, some break apart, some create tiny strands of RNA nucleotides linking, folding, pairing, unpairing, trying. Again, these strands don't think, but they do persist, and persistence is the first law of life. Picture this cell not as we know it today, full of complex organelles and machinery, but as a soft, fatty balloon, wobbly, semi-permeable. It floats at the boundary of order and chaos. It is just a container. Yes, but it contains something that behaves very differently from the world outside. Inside, information begins to flow. Not words, not symbols, but molecular whispers, shapes bumping into shapes. Some stick, some spark reactions, and when those reactions create new copies, a cycle begins, a loop, a reason to keep going. Now let us consider what this cell really is, a boundary. It holds the inside separate from the outside. This division, simple as it sounds, is profound, because in drawing that line, the cell begins to say this is me, and this identity, though primitive, is the seed of everything that comes next. Some protocells drift, some burst, some dissolve under heat or UV rays, but some by sheer chance are more stable. They last a little longer. They gather more nutrients, they contain better templates, and when they divide, they pass on that stability. This is natural. Selection, not yet life as we know it, but its ghost, its prototype, its rhythm. Now consider this. The first cell had no eyes, no brain, no purpose, yet it acted in ways that mimic purpose. It absorbed energy, it repaired itself, it made more of itself, it began to evolve. Let us pause on that word. Evolve.it means change over time guided by survival, but it also means something else, a story unfolding, a narrative told through mutations, errors, corrections, accidents that somehow led to persistence. This early cell didn't have DNA as we know it. It may have used RNA both to store information and to catalyze reactions. This RNA world hypothesis suggests that life began not with complexity, but with versatility, a single molecule doing multiple jobs, like a solo performer on an empty stage. But eventually, those performers grew tired. They needed help. Proteins began to emerge, folded chains of amino acids with specific shapes, specific tasks. Some proteins helped with copying, some protected the membrane, some increased efficiency. And over time, DNA appeared a more stable, more reliable storage system. And when DNA arrived, so did heredity, so did history, so did lineage. This moment, this transition from random replication to encoded instruction marks the true dawn of life. From this point on, life no longer simply exists. It remembers. Every cell that lives today, every skid cell, every neuron, every leaf, every bacterium is a descendant of that first moment, that first memory, that first fragile decision to enclose, to replicate, to persist. We tend to picture life as vibrant, dynamic, loud, but it began in silence, in softness, in slow, accidental steps. No music, no intention, just molecules bumping in the dark until something stuck. And so, the Earth's quiet surface bore witness to the birth of agency. From here, evolution accelerates. Cells become more complex. They learn to harness energy better. Some develop photosynthesis, filling the air with oxygen. Others become predators. Others specialize. Some even join together, beginning the long path toward multicellularity. But none of that could happen without this chapter, the moment chemistry became memory, the moment. A cell became self, and beneath it all stillness. That warm little pond, that patient earth, that silent sky, watching as the first miracle unfolded, not in fire, not in thunder, but in a bubble no wider than a speck of dust. The first cell was not aware, but it changed everything, and it is still here dotting you, in me, in every breath we take. Somewhere in the quiet moments of early Earth, when the planet was still cooling and the skies were heavy with unbreathable gases, something extraordinary may have begun beneath our feet, not in the oceans, not in the sky, but in the stillness of the rocks. Certain scientists believe that before cells existed, before even simple organic chains could survive alone, the solid lattice of minerals, especially clays and crystalline structures, may have served as scaffolding for the first organized chemistry of life. We're taught to see rocks as dead, immutable. But what if, in the early history of our world, they acted as patient teachers? Layer by layer, these minerals offered safe surfaces for unstable molecules to cling to, holding them in place while time and random chance let them find each other. When floating freely in ancient soup, these early molecules might have drifted aimlessly, breaking down before they could bond. But along a mineral's surface, they found anchors, paths, and maybe even rhythm. This theory, often called the mineral surface hypothesis, proposes that minerals didn't just host reactions, they structured them. They choreographed a primitive dance where simple molecules began forming chains, patterns, and systems. Clays, for instance, carry electrical charges. They attract specific molecules while repelling others. Their surfaces can guide chemical direction, almost like a microscopic map drawing molecules toward or away, encouraging bonds or blocking them. It's a selective process that mirrors, in a humble way, what enzymes do in modern life. Could this have been the first step toward memory? Not memory in the human sense, no stories, no thoughts, but repetition, pattern, predictability, a pathway repeated often enough that the world began to rely on it. A chain of reactions that happened again and again until it felt less like coincidence and more like inevitability. Even more curious is how some minerals seem to prefer specific left or right-handed molecules, a quality called chirality, which has baffled scientists for decades. All life on Earth today uses only left-handed amino acids. But why? Where did this cosmic preference begin? Some think the answer may lie in crystals whose structure might have subtly biased the orientation of molecules billions of years ago. One preference leads to another. Eventually, all of biology copies that pattern. Life, in a way, may be echoing a geological decision made in silence before DNA ever formed. As we explore this idea, we're not just pondering chemistry. We're revisiting a moment of balance between chaos and structure, between wild molecules and disciplined space. And in this balance, minerals may have offered something that sounds a lot like intention. It's humbling to imagine that before cells had membranes, before nature knew how to replicate, the first whispers of order were spoken not in carbon or water, but in the crystalline silence of stone, were the rocks, in some way, writing the rules. Let's stay here for a moment longer. Let's imagine these mineral plains stretching across primitive landscapes, soaked by acidic rains and warmed by volcanic breath, acting as ancient circuit boards for reactions we still don't fully understand, because in this idea, something beautiful emerges, that the Earth wasn't just the cradle for life, it was its first teacher. And if that's true, then life isn't separate from the Earth, it is Earth, crystallized, awakened, and made curious. As we walk among mountains or hold a pebble in our hand, perhaps we're touching something that once whispered the first secret of how to begin. But how did these stable chemical dances turn into something unstable, something that could grow, change, and reproduce? In the beginning, chemistry was quiet. Molecules bumped into each other randomly, bonding briefly before breaking apart. There was no direction, no memory, no goal. Just motion, just chance. But something changed, a small shift that may have echoed louder than the birth of any sun. At some unknown moment, somewhere in the deep chemistry of Earth's early days, a reaction began to sustain itself, to feed itself, and with that, the wheel began to turn. This is the strange and wondrous world of autocatalysis, where a chemical reaction produces a product that speeds up or sustains that very same reaction. Imagine a fire that throws sparks, and those sparks light more fire, or a whisper that repeats itself louder each time it's spoken, until it becomes a song. Autocatalytic reactions are special because they don't need constant help from the environment once they've begun. They keep going, accelerating on their own, sometimes even branching into more complexity. For the first time in Earth's long, chaotic chemistry, a process didn't just happen. It persisted. It amplified. It remembered. Why does this matter? Because autocatalysis introduces something new into the lifeless world, a direction. A movement from simplicity to complexity, from randomness to structure. It's not alive. Not yet. But it's not just chemistry anymore. It's behavior. Take the Formose reaction, for example. A real chemical process that starts with formaldehyde, a simple compound, and builds more complex sugars from it. One of those sugars formed can accelerate the same reaction that created it. That's autocatalysis. That's a loop, not just a line, and it's in loops that life finds its rhythm. Scientists like Stuart Kauffman have suggested that autocatalytic sets, networks of reactions that sustain and regenerate each other, could have been the seeds of life itself. In these networks, no one molecule is alive, but together as a system, they echo what life does: grow, change, stabilize, and adapt. These sets don't need a cell wall. They don't need DNA. They don't even need enzymes. They just need feedback, the ability to use their own products to strengthen their existence. That's a kind of survival. And survival, even at the molecular level, changes everything. You might picture early Earth as a giant lab bench, scattered with thousands of chemical reactions. Most of them flicker and fade, disappearing forever. But a few, the rare autocatalytic loops, keep coming back. They don't just survive, they thrive. They outcompete other reactions by using available resources faster, by building complexity, by becoming harder to disrupt. This is how evolution begins, not with genes, but with chemical persistence. The reactions that endure begin to dominate. The ones that break down are forgotten. It's an eerie thought that before Darwinian evolution ever touched biology, there may have been a kind of chemical natural selection, where loops and networks competed for space, stability, and survival, and these loops, once formed, could begin to connect. One autocatalytic network might intersect with another, passing molecules between them like shared tools. The result, a web of reactions growing larger, more efficient, more resistant to collapse. Life, in its earliest, most invisible form, may not have looked like anything we'd recognize. No membranes, no cells, just a restless field of loops, feeding themselves and each other, pulsing in volcanic puddles or clinging to mineral surfaces, trying without knowing to persist. Autocatalysis gives us a glimpse into a world where molecules began to matter, where cause and effect started to form patterns, and where chemistry began to push forward instead of just bouncing around in circles. It's in these loops that time enters the picture. Because when something persists, when something builds upon itself, the past begins to matter. What was created yesterday can change what happens tomorrow. That's not just chemistry, that's the beginning of history. A few of these reactions may have collapsed, many likely did, but others may have formed the first chemical networks that would eventually be enclosed in membranes, given energy by sunlight, and passed down from one generation to the next. All from the humble whisper of a self-sustaining loop. So what came next? Autocatalysis alone can't explain all of life's mysteries, but it sets the stage, because with loops that build complexity, nature can now store information. It can now remember. It can now replicate. There is a moment in every origin story when randomness begins to shape meaning, when chaos takes on memory, when repetition becomes instruction. This moment on the early Earth may have arrived not with thunder, but with a whisper, the whisper of a molecule that could remember its shape and copy itself. That molecule was likely RNA ribonucleic acid, a fragile strand of atoms that may have become the first messenger in Earth's long story of life. But before RNA, the world was full of loops. Autocatalytic reactions spun endlessly in volcanic pools, building sugar chains, fat molecules, amino acids, and thousands of chemical strangers. Some of these reactions survived longer, others died quietly in the mud. But what none of them could do, at least not yet, was carry information forward with precision. Autocatalysis created persistence, but RNA introduced instruction. Imagine a strand of RNA lying in a shallow pool. It's not much to look at, just a chain of smaller molecules called nucleotides, each with one of four chemical letters, A, U, C, and G. But those letters can form patterns, and patterns can be read. More importantly, those patterns can be copied. In that moment, chemistry takes a leap. Now, reactions aren't just happening, they're being guided. Blueprints are emerging from the randomness. The universe has invented code, and RNA, it seems, can do more than just carry this code. It can also act like a primitive machine. Certain RNA molecules known as ribozymes are able to fold into complex shapes that can catalyze chemical reactions. In other words, RNA was both the message and the messenger, a rare duality that made it immensely powerful. This idea that life may have begun in an RNA world is not just speculation. It's one of the most widely discussed theories in the study of life's origins. The theory suggests that RNA was the bridge between raw chemistry and biological life, a molecule that could copy itself, mutate, evolve, and even catalyze reactions, all without proteins or DNA. Proteins, the molecular machines of modern biology, came later. DNA, the stable vault of life's blueprint, came later. But RNA, it may have walked alone in the beginning, laying the tracks that others would follow. But RNA is delicate. It breaks down easily in water. It's unstable compared to DNA. So why do scientists believe it came first? Because of its versatility. RNA can copy short sections of itself. It can catalyze reactions. And in controlled experiments, researchers have watched it evolve in real time, changing shape, finding shortcuts, solving problems. It may be fragile, but it's clever. In the deep past, simple strands of RNA might have formed spontaneously on mineral surfaces or within fatty bubbles that offered shelter. Some of these strands may have had just the right shape to speed up their own replication. If one copied itself slightly better than the others, it would begin to dominate the chemical landscape, not because it was alive, but because it endured. And here, a new kind of evolution begins, not just selection among reactions, but selection among patterns. The first code war, the first competition of messages. Suddenly, chemistry has a memory. Molecules have lineage. Each new strand of RNA is not just a random structure, it is a descendant, shaped by what came before. And with memory comes mistakes. Every copying process includes errors. These mutations, as they're now called, are the source of change. Most are harmful, but some led to better replication, better folding, better chemistry. These mistakes become the tools of progress, the first sparks of evolution by natural selection, not in animals or plants, but in naked strands of molecules, floating in the warm shallows of Earth's first oceans. We don't know exactly when RNA began to pair with proteins, or how DNA eventually took over as life's archive. But we know this. The emergence of an information-carrying molecule was a turning point. Before RNA, life was a looping whisper. After RNA, life became a story, a process that could remember, improve, and build upon itself. One strand begat another, and another, and another. And those strands learned to fold, and those folds began to help. And in time, the chemistry that once only danced began to think. In a way, RNA was the first primitive mind, not a conscious one, but a system capable of influence and memory, selection and change. It laid the groundwork for every brain, every neuron, every sentence, and every dream. As strange as it sounds, your ability to read these words might trace its roots back to a molecule that once floated alone in a silent pool, whispering its shape into the future. What if the ocean wasn't just a body of water, but a vast chemical womb, warm and whispering, filled with ancient secrets and molecular dreams? As we drift gently into this chapter, Imagine a time before organisms, before even the concept of biology existed. Picture the Earth wrapped in thick clouds of volcanic steam, its surface still scarred from relentless asteroid impacts, its skies dark and hostile. And yet, somewhere in the cradle of this chaos, the oceans shimmered with potential beneath those primeval waves. The seas were not silent. They were teeming with interaction, simple molecules colliding, combining, breaking apart, and trying again. Water, after all, is not a passive participant in chemistry. It dissolves, it mixes, it provides a stage for reactions to happen. In these oceans, chemistry didn't just occur, it learned. Slowly, almost imperceptibly, it began to remember. Here, the story of life teeters between chance and certainty. The first important players were not living things, but rather fragments of potential amino acids, nucleotides, fatty acids. These tiny building blocks likely rained down from space aboard comets and meteorites, while others were forged here on Earth in the boiling womb of underwater volcanic vents or lightning-lash ponds. In these rich soups, something remarkable happened. Molecules didn't just float, they began to interact with purpose. Fatty acids self-assembled into tiny bubbles known as micelles and protocells, each forming a microscopic boundary that trapped other molecules inside. This wasn't life, not yet, but it was organization. It was the first whisper of structure, the earliest suggestion of containment of inner and outer worlds. Hydrothermal vents, those black smokers deep beneath the sea, blasted scalding water, filled with iron, sulfur, and energy. Around them, chemistry bloomed in ways the surface could never match. These vents offered the essential ingredients for complex molecules: stable heat, catalytic minerals, and the shelter of deep pressure. Within their mineral-laden walls, simple carbon molecules began linking into longer chains, forming sugars, peptides, and rudimentary polymers. It's tempting to imagine these molecules stumbling upon each other like strangers in the dark. But, in truth, they were caught in cycles. Cycles that returned, cycles that repeated. These chemical loops began to favor certain reactions over others. Some compounds lasted longer. Some could even help form more of themselves. Replication was no longer a distant dream, it was beginning, subtly, in the background. Think of it, not a single spark, but a slow rise of complexity. A gradient, not a jump. Life did not begin with a bang, but with a whisper, persistent, cyclical, and gradual. The oceans, rich with energy and time, became a cauldron for self-organization. As certain molecular shapes proved more resilient, more stable, they began to dominate. Nucleotides formed chains of information, RNA, perhaps even before DNA. These chains could copy themselves, not perfectly, but well enough. And with every imperfect copy came variation and opportunity for evolution to peek in. Meanwhile, fatty acid membranes continued evolving. Some began to trap these information molecules inside their watery bellies. These primitive enclosures, early versions of cells, weren't alive by our standards, but they exhibited behaviors, absorbing, excluding, reacting. They mimicked life in all but name. Could these protocells grow, divide, pass on their contents? Evidence suggests they could. And so, the boundary between chemistry and biology grew thinner. The line blurred. As these bubbles became more sophisticated, internal chemistry grew more complex. RNA molecules didn't just copy, they catalyzed. They sped up reactions, helped organize interior chaos, and laid the groundwork for something truly astonishing. Self-sustained metabolic cycles. Imagine floating through that ancient sea, watching as bubbles form, split, and reform. Inside, molecules shift, interact, and sometimes, by accident or design, survive. And those that survived carried with them the memory of success, a whisper of natural selection long before genes took over the story. We must remember, none of this happened overnight. These processes unfolded over millions, perhaps hundreds of millions of years. The world didn't wake up to life, it slowly turned toward it, one molecular choice at a time. And yet, isn't it beautiful? that something as alive as us can trace its roots to non-living chemistry, that consciousness, emotion, memory, all find their deepest ancestry in the silent experiments of a planet's oceans. As we let this chapter settle like mist on still water, consider this. Are the oceans still whispering? Do the tides remember? When you drink a glass of water, does some ancient pattern echo in its molecules something older than bones, older than breath? Perhaps even now, in some unexplored corner of a deep-sea trench, new whispers are beginning. Whispers of a second Genesis, whispers that one day someone else or something else might listen to. The quiet world before life was not truly silent. It was filled with signals, but no one to hear them. The earliest chemicals drifted, collided, and rearranged not randomly, but with subtle patterns, like a whisper passed between strangers in the dark. Over time, those whispers grew louder. Information started to accumulate. A chain of cause and effect began to mimic meaning, and meaning, eventually, became memory. In the earliest stages of Earth's pre life era, the oceans were like a giant experiment waiting to unfold. Imagine molecules scattered like puzzle pieces across vast stretches of mineral-rich water, stirred by volcanic heat, lit by ultraviolet flashes, and kissed by the currents of a young, restless planet. These were not yet alive, but some had preferences. Some molecules clung to certain surfaces more than others. Some combined with metals. Some resisted decay. These little tendencies, barely noticeable, began to add up, like letters forming syllables. These molecules were forming patterns. They weren't just floating anymore. They were beginning to respond, and in that subtle responsiveness lay the first primitive gestures of communication. Think of it this way. If life is about information, about encoding, storing, copying, and reacting to signals, then long before cells or membranes or DNA, there must have been signals without senders, structures that began to retain the memory of reactions. Some molecules folded in ways that helped others fold. Some sequences catalyzed their own replication. These weren't cells yet, but they were messengers. Science calls this stage chemical evolution. It's the slow transition from passive matter to active systems. No genes, no metabolism, just sequences that persisted because they accidentally copied themselves better than others. But that accident wasn't just luck. It was structure favoring pattern, and pattern favoring memory. And so we come to a speculative threshold. What if memory began before minds? Ribonucleic acid RNA is often considered one of the earliest molecules that could carry information. It's more than just a chemical. It's a self-copying structure. RNA doesn't just sit still. It bends, loops, links with other molecules. In labs today, we've seen how RNA-like strands can emerge from simpler chemicals, given the right conditions. It's not magic, it's repetition. And from repetition, language is born. In the deep past, maybe millions of these proto-strands formed and fell apart, but some folded just right, not too tightly, not too loosely, and began to stick around. Those that persisted shaped the behavior of their environment, and in doing so, the environment shaped them back. This slow dialogue, repeated over eons, became something more, emergent instruction. Imagine the earth itself as a kind of incubator, not just of life, but of meaning. Over time, the ocean's chemistry may have started recording lessons. Which chains were more stable, which combinations reacted faster. These lessons weren't written in books. They were etched into molecules, encoded in shapes, bonds, and sequences. This raises an unsettling and beautiful thought. What if the Earth began to listen to itself? Not consciously, of course, but in a mechanical, evolutionary sense. The planet, through its heat and minerals and fluids, was providing both chaos and order. Within that feedback loop, information began to echo. Some echoes lasted longer than others, and the longer they lasted, the more they influenced what came next. Over millions of years, these tiny chemical signals may have formed the first grammar of life, a silent molecular syntax from which everything else emerged. You might picture it like this. Before life spoke, chemistry whispered, and slowly, through those whispers, A system emerged that began to respond to the environment rather than just exist within it. And that's a subtle difference, but a powerful one, because to respond is to make a choice, even if it's chemical. And choices, however small, are the roots of behavior. Behavior becomes habit. Habit becomes system. System becomes organism. This chapter, then, invites us to ponder a quiet possibility that molecules didn't just bump into each other until something worked. They evolved toward expression, and if that's true, then perhaps the origins of life were not a single moment or miracle, but a slow awakening not of organisms, but of communication itself. The molecules learned to speak, not in words, not in thoughts, but in structure, in pattern, in memory, and from that first whisper, life began to stir, not with a shout, but with a soft repetition, an echo. Before anything could live, it had to be set apart from everything else, not with intention, not with design, but with a gentle accident of chemistry. You see, in the warm, restless oceans of the early Earth, something strange began to happen. Again and again molecules, particularly fatty ones, would gather. They were simple structures, each with a head that liked water and a tail that hated it. So when they found themselves surrounded by liquid, they began to form circles, and then spheres, bubbles really, nothing more. But these bubbles made of fatty acids and lipids were different from anything that came before, because they created something the universe had never known until that moment, an inside and an outside. A subtle distinction, but one with enormous consequence. For the first time, matter wasn't just drifting through space or sloshing in soup. It was contained, and containment changed everything. When molecules are trapped together, something magical begins to happen, not by will, but by proximity. Reactions that might never occur in the open sea start to happen more often. Chains of atoms begin to loop, fold, or spark. Conditions grow more stable, less chaotic. The tiny bubble becomes a quiet little world, a pocket of order within the storm. These early structures weren't alive. Not yet. They couldn't reproduce, think, or adapt, but they could hold, they could shelter, they could provide the first real stage upon which life might one day perform. Scientists call them protocells, not true cells, but their ancestors. They were the scaffolding upon which biology would one day build itself. Think about that for a moment. The very first cell-like things on Earth weren't complex at all. They were as simple as a soap bubble, just a thin film surrounding water. But in that film, molecules began to be protected from degradation. Random strands of RNA might have entered and been preserved. Small catalytic minerals might have slipped. Inside, chemical gradients differences between inside and outside began to emerge, and with those gradients came potential, because a difference in nature is opportunity. A battery works because it has a charge imbalance. A muscle contracts because it moves ions across a barrier. Even your thoughts right now are nothing but electric charges dancing across membranes in your brain. All of that starts with a separation, a thin line between what is me and what is not me, and that line began with a bubble. In the sea, over time, these bubbles may have merged or split. Some grew bigger, engulfing pieces of clay or metals or small chains of carbon-based compounds. Others may have collapsed quickly, but some by sheer chance held together just long enough for something new to form inside. Perhaps a strand of RNA that could copy itself. Perhaps a molecule that sped up a reaction. Perhaps the beginnings of metabolism. We don't know the exact moment the first living cell appeared, and maybe there wasn't one single moment. Maybe it was a gradual climb from chemistry to protocell, from protocell to something more. But we do know the war came first. The boundary, the membrane, the shelter, and that shelter was never passive. Cell membranes today are dynamic. They aren't solid walls. They're more like active gates. They let things in. They pump things out. They respond. They even send messages. All of that complexity began in those early enclosures, when nature first stumbled on the strange trick of wrapping liquid in fat. Even the earliest membranes might have had semi-permeability, the ability to let some things through, but not others. That's critical, because it means certain molecules could concentrate inside, while harmful ones stayed out. Imagine a tiny protocell floating in a warm tide pool, absorbing sunlight and trace nutrients. Maybe it's been stable for an hour, maybe for a day. Inside, a strand of RNA starts to make a copy. Not perfectly, but close enough. That's huge. That's memory. That's the beginning of inheritance, one molecule teaching another how to be. But without the membrane, that strand would drift away, broken apart by the C.O the bubble holds it. Not tightly, not forever, but long enough. And when that protocell becomes too large, it might split in two. Not on purpose, just from instability. The bubble tears, and two smaller ones drift away, each with part of the original contents. That's not reproduction as we know it, but it's a step toward it, and steps add up. Over millions of years, the bubbles that held together best would have become more common. The ones that housed useful molecules would have passed on their traits. Natural selection didn't need to wait for DNA or even life. It could begin right there with bubbles competing for persistence. And here's something wild. Even today, researchers can create protocells in the lab. They mix fatty acids in water, adjust the pH, and watch as little vesicles form. Some can even enclose RNA or other polymers. It's eerie, it's beautiful, and it's deeply humbling, because it shows that life's first containers weren't miracles. They were inevitable. Given the right ingredients and enough time, you might wonder, what held these protocells together? What kept them from dissolving in the turbulent sea? The answer is chemistry, once again. Fatty acids prefer to be together in water. They form bilayers just like our own cell membranes. And over time, nature would have discovered better lipids. Stronger, more stable ones until the modern phospholipid bilayer emerged. That's what your cells are wrapped in now. Every one of them. A thin, flexible film that traces its ancestry back billions of years to a tide pool where fat met water and made a wall. But that wall was never meant to isolate. It wasn't about building a prison. It was about creating a space where life could try, fail, repeat, and remember. Inside the protocell, reactions became more efficient. Catalysts stayed near their substrates. Loops formed, chains linked. Energy was captured, used, released, and soon those bubbles weren't just holding reactions, they were guiding them. They were organizing. They were beginning to resemble something that might, just might, one day evolve. We take this for granted now, because cells are everywhere. Every blade of grass, every bacterium, every drop of blood is full of them. But they all began with a simple lesson from the ancient sea. To survive, something must first be separate, not cut off, not alone, but distinct, defined, sheltered. And so the membrane became life's first home, a flexible boundary, a chemical whisper, a bubble that breathed. Maybe it didn't know what it was, but it held the first sparks of identity, and without it, nothing else could have followed. Long before there were lungs to breathe or eyes to see, the earth stirred with invisible storms, not of wind or water, but of energy, chemistry, and slow transformation. And somewhere in that hidden dance, beneath layers of rock and ocean, far from the light of stars or sky, something profound began to unfold. This is where we journey now into the protected crevices and warm fractures of Earth's ancient crust, where life may have first found shelter and purpose. They call them hydrothermal vents, deep sea chimneys of heat and minerals, formed where the planet's crust fractures and seawater rushes in to meet magma. But to imagine them simply as cracks spewing heat is to miss their ancient poetry. These vents are alchemical cauldrons, releasing hot, mineral-rich fluids into freezing ocean depths. Temperatures can swing from scalding to icy within centimeters, creating gradients, delicate differences of energy and matter. And in nature, gradients are invitations for transformation. Think about this. Life as we know it depends on boundaries, membranes that separate, gradients that flow, walls that hold. Every living cell is a container of contrasts. So what if, in these ancient underwater cathedrals, the same principles began to assemble? Some scientists believe that alkaline hydrothermal vents, with their porous walls and slow chemical flows, could have created the perfect staging ground for PI life chemistry. Imagine tiny rock pores microscopic cavities acting like early cells, containing and concentrating molecules, allowing reactions to repeat, refine, and remember. Within these mineral wombs, carbon molecules might have met metals, phosphates, and heat. Reactions may have been guided by the labyrinthine architecture of stone itself. Unlike the chaos of open oceans, here was shelter, not a warm pond, but a protected architecture where the heat of Earth's belly met the chill of ancient seas. The theory is called the vent hypothesis, and it's hauntingly elegant. It tells us that life didn't begin in stillness, but in gradients, in movement. In contrast, proton gradients, in particular, are central to life's energy systems, even now in your cells, in plants, in bacteria. It's possible that life inherited this electric whisper from the very first moments, not by design, but by environmental necessity. Life learned to live on the edge of a current. And maybe this is the core mystery we often miss, that life is not a thing, but a flow, a pattern carried forward, a ripple that found a way to echo. But not all vent systems are alike. Black smokers, for example, spew superheated water filled with metals like iron and sulfur, forming towering columns of dark mineral. They appear apocalyptic, dramatic, and yet, around them, even today, strange creatures thrive. Worms with no mouths, crabs with no eyes, ecosystems divorced from sunlight, surviving solely on chemosynthesis, life feeding not on light, but on Earth's inner breath. It's humbling to realize that life doesn't need our rules. It doesn't need sunlight, or oxygen, or a blue sky. It just needs a gradient, a membrane, a possibility. And in the deepest silence of the sea, where time moves slowly and heat pulses like a heartbeat, these ancient conditions still exist, still inviting, still forming, still waiting, perhaps, for life to begin again. But what if we zoom further in, zoom past the vents, into the cavities of rock, into the lattice of minerals like serpentine, olivine, and iron sulfide, which can catalyze reactions all on their own? The walls of these rocky pores might have acted like early enzymes, helping basic molecules assemble, align, and transform. Structures like graphite and iron sulfur mineral have even been proposed as scaffolds for primitive metabolism, able to trap carbon, hold electrons, and perhaps even mimic the cause of modern enzymes. What emerges is a portrait not of chaos, but of slow precision. Nature as a patient sculptor, not with hands but with time, temperature, and tectonics. 100 million years could pass in these mineral veins, with reactions repeating endlessly, until one day a self-sustaining pattern arises. Something that resists entropy, however slightly. Something that can copy itself. Something that endures. Now imagine this, in these vents. Between the sharp shifts of temperature and pressure, tiny bubbles of fatty acids may have begun to form simple spheres with watery interiors. Primitive versions of membranes. These bubbles could trap molecules inside. They could divide, merge, evolve. Could this be the moment when geology turned into biology? When chemistry wrapped itself in a boundary and whispered, "Begin again"? We do not know for certain, but the clues are mounting. In 2016, scientists discovered that simple RNA-like molecules could assemble on the surfaces of minerals, under vent-like conditions, without enzymes, without DNA, without life. These are not myths. They are experiments, replicable, observable, and they bring us one step closer to understanding how the inanimate world may have awakened. But there's something even deeper, not in the science, but in the metaphor. These vents, these cracks, in Earth's surface, they are not flaws, they are beginnings. They remind us that sometimes the most profound transformations happen not in peace, but in pressure, not in light, but in shadow. And perhaps the origins of life are not a singular spark, but a threshold crossed slowly, with false starts, with echoes, with persistence. Is we port here, at the mouth of the vent, the water around us cold, the minerals glowing faintly with inner heat, and we wonder, if the Earth could create life once, could it do so again? And what are the worlds with their own vents? Their own gradients might be gestating something now in silence. Because if life began here not as a miracle, but as a consequence, then perhaps life is not rare. Perhaps it is what happens when a planet breathes deeply and waits long enough. Perhaps there are cradles beneath storms across the universe, and we are only beginning to remember where we came from. What if there was a moment, not just of chemistry, but of transformation? A moment when the chaos of molecules leaned in close enough to the edge of organization, and just for a heartbeat, they didn't fall apart. What if that heartbeat never stopped? We often imagine the origin of life as a spark, a sudden miracle, a divine flash or a bolt from the sky. But nature rarely works in absolutes. It dances in gradients, moving slowly, hesitantly, across boundaries we cannot always define. And life, real life, not the poetic idea of it, but the cellular, dividing, metabolizing thing. It may have arisen not from one miracle, but from a long, slow accumulation of tiny ones. By the time we arrive at the birth of the first true cell, the Earth is already ancient, over 4 billion years old. Volcanoes still churn and spit. The oceans still boil and cool. Tides still carry the whispers of elements against the rocks, grinding and shaping and stirring. Somewhere in this restless world, inside a tiny, fatty bubble perhaps only micrometers wide, the right collection of molecules has finally formed a system that can replicate, feed, protect, and persist. It is no longer a hopeful accident. It is a unit. It is alive. We call it the protocell. But it was likely more than a proto, more than a simple precursor. It was the dawn. This tiny structure may have looked like nothing more than a microscopic droplet, but inside it contained the world's first true home for life. A membrane, a metabolism, and genetic information, all housed within one soft, self-contained vessel. This was not just chemistry anymore, it was biology, and yet it would not have looked like anything we'd recognize today. The earliest cells were almost certainly what we now call prokaryote organisms without a nucleus, without the elaborate organelles that define more complex life, just a bag of molecules inside a boundary. But within that bag was everything, a pattern that could copy itself, a barrier that could protect itself, a process that could feed itself, and most importantly, the ability to persist across generations. The magic was not perfection, it was stability, persistence, continuity, because now, for the first time, there existed a structure that could survive, change, and pass on the instructions for itself to another. That ability to pass along memory. Not just molecule was the hinge upon which life turned out. It likely didn't happen in a single place, or at a single moment, across the planet, wherever the right conditions brewed, whether near volcanic vents, inside mineral pores, or along tide pools kissed by the moon's pull. Dozens, hundreds, maybe thousands of these early living systems may have flickered into being. Many would vanish, some would split apart, some might fuse, but a few would endure, and in enduring they would begin to evolve. This was the moment evolution could truly begin, not in the abstract, but in action. Natural selection no longer operated only on random chemistry, but on reproducing systems, on lineages, on ancestors and descendants, on survival, on error, because the earliest genetic systems were crude. RNA strands were short, error-prone, vulnerable to breaking. But in their imperfection lay the secret of progress. Mutations happened. Some were catastrophic, but others made the protocell better, more efficient, more stable, more capable of drawing energy from its surroundings or protecting itself from danger. And when those improvements were passed on, they became the new baseline. A ratchet had formed. Life was climbing over time. The landscape of possibilities widened. Protocells with better lipid membranes survived longer. Ones with more reliable replication copied themselves faster. Ones that could metabolize simple molecules into useful energy grew larger or divided more often. And slowly, a branching tree began to take shape. The first divisions of life, not just into individuals, but into lineages, We speak of Luca, the last universal common ancestor, as the being from which all life today descends. But Luca was not the first living thing. Luca was likely the soul, survivor of a great crowd of early life forms, a descendant of survivors, carrying the genetic memory of 1,000 near lives that came before. When we look back at Luca, we don't see a single miracle, we see the one branch that didn't break. Luca, based on evidence, likely had already developed sophisticated features, a genetic code, a rudimentary form of protein synthesis, perhaps even early cellular machinery. By then, life had already been running for hundreds of millions of years. The raw miracle of first life had faded into the ordinary miracle of continuity. But we cannot help wondering, what did that first true cell look like? Could we ever reconstruct it? Would it feel like meeting a ghost? In laboratories today, scientists have attempted to create protocells, artificial compartments of lipids filled with simple RNAs and metabolic molecules. They watch them swell, divide, sometimes even replicate. But even these are only echoes, our best guesses at what might have been. The original remains elusive, not because it's hidden, but because it was not one thing. It was a process, a gradient, a direction. Still, we chase it. We build models, simulate conditions, recreate tidal cycles and hydrothermal flows. We display surfaces and pH gradients and iron-sulfur membranes. Because somewhere inside those quiet reactions, something profound happened. Matter developed memory. Chaos developed pattern. A dance became a rhythm, and rhythm became life. And when that first rhythm began to copy itself, when it lasted long enough to become something persistent, it marked a new kind of time, not the time of stars or gravity or motion, but biological time. Time measured in generations, in trial and error, in memory and mutation. The emergence of the first cell did not reset the clock. It changed the kind of clock we follow. Now, instead of just watching geology unfold in passive erosion, the Earth was hosting a new kind of force replicators that learned, that competed, that expanded and spread and carved their own mark into the rock. And in a very real way, we are those marks. Every cell in your body, every strand of your DNA, every fold in every protein, every breath you take is built on that original rhythm. You are not separate from the first celluloids. Echo, billions of years later. So we sit now, suspended between awe and humility. We do not know the exact moment life began. We do not know whether it was a single droplet or a swarm, a bubble on a beach or a fissure in the ocean floor. But we do know that it happened. We are the proof, and if it happened once, quietly, under alien skies on an early Earth, perhaps it can happen again, elsewhere, in places we cannot see. But for now, we honor the hidden past, the invisible threshold where matter learned to remember, where energy found order, where stillness broke into motion, where, at last, the long sleep of the universe stirred and opened one tiny, trembling eye. The Earth was never a still sculpture. It was always melting, churning, falling into newer versions of itself. And as we drift further down the timeline, we begin to notice something strange, a quiet force, constantly rearranging every molecule in the universe. That force is entropy. Entropy is not chaos. It is the gradual unbreeding of order, the natural tendency for all things to lose their structure and slip into a more probable, less organized state. You see it in the way ice melts into puddles, how cliffs crumble into dust, and how even memory becomes blurry at the edges of time. What does this mean for the origin of the first living cell? We often imagine life as a victory against disorder. But what if life was actually born because of entropy, not in defiance of it? Could it be that the first cell didn't fight the collapse, but was part of a deeper flow and eddy in the river of increasing disorder? On the early Earth, everything was hot and full of tension. Volcanoes tore at the seams of continents, oceans steamed and churned with minerals, and sunlight rained down in ultraviolet sheets. All of this created contrast, differences in heat, energy, and concentration, exactly what entropy feeds on. Imagine a little pocket forming in this world. Perhaps a simple bubble of fat enveloped a few molecules by chance, nothing special. But inside that membrane, the chemical reactions didn't stop. They flowed, spiraled, interacted, in a world slipping toward disorder. This pocket became a temporary island of organization, not because it was meant to, but because the laws of thermodynamics allowed it, perhaps even demanded it. Entropy isn't destruction, it's movement, and life at its core is movement too. The cell metabolizes, transforms, reacts. It doesn't preserve stillness, it orchestrates flow. Just like a waterfall doesn't defy gravity, but dances with it. The first cell may not have resisted entropy. It may have ridden it. This opens a new kind of question. What if the architecture of life is shaped by collapse? Take, for example, the mitochondria, the energy center of our cells. It was once a free-living bacterium, swallowed by another cell billions of years ago. But instead of being digested, it stayed. It collapsed into a smaller role and became indispensable. Or DNA itself, twisted like a ladder snapped into a spiral. Its very structure is designed to break in controlled ways, to allow replication, repair, evolution. In the deepest sense, life appears to be a cooperation with entropy. It builds patterns that are destined to fall apart, only to build them again, just like mountains rise and erode, only to rise again. Somewhere else, you might wonder, why does this matter for understanding the first cell? Because it helps us stop looking for a singular miracle. Instead of imagining life as a bolt of lightning hitting the perfect puddle, we can imagine it as something softer, gradual, repeating, a pattern that formed and reformed across billions of attempts until one configuration stuck around long enough to leave a trace. Entropy becomes the artist, here not a villain, but a sculptor. It removes what cannot last, it rearranges what remains, and it favors the emergence of things that can flow. That includes rivers, and that includes life. The river never repeats its shape, yet it never stops flowing. We are often drawn to permanence. We like to think the first cell was something solid, an endpoint, a success. But maybe it was more like a swirl in the current, temporary, fragile, but meaningful, because it was part of a deeper story. Entropy also explains why death is inevitable. Every living thing runs down, cells wear out, DNA accumulates errors, energy dissipates. In the end, even stars go dark. But in this collapse, there is continuity. The death of one star seeds the birth of new planets. The death of organisms creates soil. The entropy of one system powers the emergence of another, just as collapsing cliffs feed rivers with sediment. The decay of molecules fuels new reactions, new bonds, new forms. Even today, our own bodies are not closed systems. You breathe in oxygen that was once inside a volcano, each carbon that once drifted in the air, and the molecules that make you your bones, your thoughts. Your cells are slowly becoming other things. We are not fixed. We are part of this slow surrender to entropy. And if we carry this lens backward in time, to the moment before the first cell emerged, we find a world not waiting for a miracle, but already in motion. A planet filled with gradients, hot to cold, acidic to alkaline, deep to shallow. Every boundary became a testing ground, every contrast a canvas. Maybe the question isn't, how did life begin? But how did entropy carve something so intricate? Let's revisit hydrothermal vents, those boiling chimneys on the ocean floor. They spew hot, mineral-rich fluids into cold seawater, creating massive energy gradients. That's entropy's playground. And right at the boundary of these flows, we find something astonishing. Little rock pores that act like natural cell membranes, cycling fluids in and out, concentrating chemicals, building complexity. It's not far-fetched to think that the first metabolic reactions happened there, and not as exceptions, but as inevitabilities if given enough time and flow. In this view, life isn't rare, it's patterned, not in the way crystals form from repeating shapes, but in the way music forms from contrast, tension, and release. Life becomes a rhythm in entropy's orchestra. The cell becomes a verse in a song the earth has always been humming. This also softens our view of time. We no longer see a straight line from chaos to order, but a loop. Entropy doesn't destroy meaning, it reveals it. Every collapse teaches the system to try differently next time. Every ruin becomes soil. Every mistake becomes feedback. The first cell may have been the result of a billion failures, but each failure carried information forward, and entropy was the teacher, quiet, indifferent, but precise. So when we look around and wonder why we're here, why anything exists at all, we might look not to the stars, but to the quiet breakdown of things, because in that breakdown, life finds a way to reorganize, to express, to persist. We are not built despite entropy, we are built through it. And perhaps in the last analysis, entropy is not the story of decay, but the story of becoming, because when everything falls apart, something else gets to begin, and maybe, just maybe, that's how it all started. In the quiet, hazy oceans of a young Earth, a profound shift was stirring, not with thunder or tremors, but in the faint ripple of invisible molecules, drifting in gentle currents beneath the waves. The surface world, still battered by ultraviolet radiation and often shrouded in volcanic ash, knew nothing yet of the revolution blooming silently in the shallows below. Until this point in Earth's history, life had existed in darkness, relying on chemical gradients near hydrothermal vents, or fermenting organic molecules in murky pools. But something was about to change. Life was about to turn toward the light, literally. And with that, the blueprint of the entire biosphere would slowly begin to rewrite itself. Let us drift down into these primordial waters, into a time before green forests and coral reefs, before fish, swam or insects flew, when life was still microscopic and drifting, and follow the quiet rise of photosynthesis, the process that would allow living cells to harvest sunlight, breathe out oxygen, and eventually shape the very skies above us. It began, humbly, with tiny organisms, cyanobacteria, often called blue-green algae, though they were not algae in the modern sense, but ancient prokaryotic cells that had learned a new trick. Unlike their anaerobic cousins, these cells contained pigments capable of capturing solar photons, little packages of light energy, and using that energy to split water molecules. This was unprecedented. The splitting of water released oxygen as a byproduct of waste gas, in a way but one that would have catastrophic and magnificent consequences for the planet. Imagine these early microbes, floating in sunlit shallows, multiplying slowly, their pigments early precursors to chlorophyll, absorbing sunlight and channeling it into chemical reactions, turning carbon dioxide and water into glucose and oxygen. They were, in effect, small factories of transformation, using starlight to power molecular change. For eons, the Earth's atmosphere had been a toxic, reducing environment filled with methane, ammonia, and hydrogen, but very little free oxygen. Life had evolved to thrive in this alien soup. Oxygen, in fact, was poisonous to many early microbes, but photosynthesis didn't care. It kept working, day by day, releasing bubbles of O into the water. At first, the oxygen didn't accumulate. It reacted with dissolved iron in the oceans, oxidizing it and creating rust, which then sank to the seafloor, forming vast bands of iron deposits that we still mine today. This stage, called the Great Rusting, continued for hundreds of millions of years. Ocean after ocean, iron was oxidized and stripped away. Only once the iron was depleted did oxygen begin to accumulate in the oceans, and then, eventually, in the air. And that moment, slow and invisible though it was, marked the beginning of Earth's greatest atmospheric transformation. You might imagine that this was a great leap forward, and in a sense, it was. But to many of Earth's existing microbes, it was a death sentence. The oxygen released by photosynthetic organisms was toxic to anaerobic life. It damaged their proteins, broke apart their DNA, disrupted their membranes. Many ancient species went extinct. Whole ecological systems collapsed. This mass extinction, known today as the oxygen catastrophe, was one of the first major biological crises Earth would endure. And yet, out of this crucible of chaos came opportunity. Some organisms adapted, developing ways to detoxify oxygen, or hide in oxygen-free environments. Others evolved enzymes like catalase and superoxide dismutase to protect themselves. Still others made a bigger leap. They learned to harness oxygen's power because oxygen, though dangerous, was also incredibly potent. It allowed for much more efficient energy production. Instead of extracting just 2 ATP, the cell's energy currency per glucose molecule, like anaerobic fermentation, oxygen-based respiration could extract 36 or more. This surplus energy opened new doors. Suddenly, cells could grow larger, build more complex internal machinery, reproduce more efficiently, and store energy for longer. Oxygen had changed the rules of the game, and photosynthesis had written the new rulebook. Let us drift again through time. Imagine shallow tidal pools rich with cyanobacteria, their colonies forming thin, sticky mats. Layer after layer, these mats build up over time, becoming stromatolites. Rocky structures made from microbial life itself. These stromatolites are among the oldest fossils we have on Earth, some over 3.5 billion years old, and they still exist today. In a few isolated places like Shark Bay in Australia, they are living time capsules, carrying the signatures of a time when life was small, slow, and alien, but unimaginably resilient. Each day, as the sun rose over the horizon and filtered through clouds of volcanic ash, these mats would activate, capturing sunlight, performing photosynthesis, and releasing bubbles of oxygen into the water. Slowly, imperceptibly, the balance of the planet shifted. Skies once opaque with methane began to thin. Oceans changed their chemistry, and high in the upper atmosphere, something else began to form, a protective layer of ozone, built from oxygen molecules that could shield the surface from ultraviolet radiation. This, too, was a quiet miracle. With the formation of the ozone layer, life no longer had to hide in the depths, the surface of the ocean, and eventually, the land became habitable. Photosynthesis had not just changed the chemistry of the air, it had opened the door for life to move upward, outward, and eventually onto land. And so, from the tiniest pigment-bearing microbe came a cascade of transformation, a process born in the water that changed the sky, a quiet chemical whisper that rewrote the rules of life. Photosynthesis did not emerge overnight. It took hundreds of millions of years to spread and dominate. But once it did, it became the engine behind forests, meadows, algae blooms, and even the grass beneath our feet. And its fingerprints are everywhere. Every breath you take, every apple you eat, every flicker of green in your vision on a summer day carries the legacy of that ancient revolution in the grand story of life. There are moments of noise, asteroids, extinctions, fire, and flood, but there are also moments of silence, where the only sound is the sun touching water and the slow unfolding of a new idea. Photosynthesis was one of those moments, and though it began as a whisper, it would soon become the breath of the world. It is easy to take boundaries for granted. In the modern world, boundaries define everything: walls that divide rooms, skin that protects organs, even the invisible edge between your inner thoughts and the world outside. But before there were boundaries, there was only the blur. Before life became something recognizable, something structured, something breathing in and out in delicate cycles, Earth was merely a bowl of possibilities, a place where complex molecules drifted through primordial waters without purpose, colliding, dissolving, reforming, then dissolving again. For life to emerge, something radical had to happen. Those drifting molecules needed to find shelter. They needed walls. They needed homes. The cell, the basic unit of life, is not just a bag of chemicals. It is a boundary, a membrane, a shell that both protects and allows, lets things in, keeps things out. But how did this vital structure arise? How did the very first cell envelope come into being? Long before evolution had any hand in sculpting membranes with intention, let's drift back to those ancient warm ponds, rich with fatty acids and oily films. These simple molecules, not living and not dead, had one peculiar trait: they didn't like water, or more precisely, only parts of them liked water. Fatty acids have two ends, one that is hydrophilic, which means it loves to dance with water, and another that is hydrophobic, that recoils from it like a shy creature. In the ancient seas, this tension played out endlessly. Every time fatty acids entered water, they twisted and flipped, trying to shield their fearful ends from the surrounding wetness. Then came the miracle, unintentional, yet fundamental. These molecules began to self-assemble, not through will or thought, but through chemistry. They formed micelles, tiny spheres, each with its water-loving heads pointing outward and water-fearing tails tucked safely inside. Then some spheres grew larger, flattening into bilayers, then curling inward until they formed vesicles, tiny bubbles, small pockets of safety suspended in chaos. It was within these simple vesicles that the first whispers of life found refuge. Imagine it. A molecule that had once drifted freely, always vulnerable to dilution or destruction, now finds itself enclosed safe within a fatty bubble, protected from the outside world. Inside that small chamber, reactions could last longer, experiments could repeat, and molecular partnerships could be tested without interference. Suddenly, there was a place for complexity to grow, a pocket where the dance could deepen. This enclosure, this accidental birth of boundary, was not life yet, but it was the first echo of organization. It meant certain chemicals could stay together long enough to perform reactions that mattered. Perhaps one vesicle trapped a strand of RNA, and that RNA began to copy itself. Perhaps another carried catalytic peptides that stabilized certain processes. The vesicle, with its soft walls, became a stage, and on that stage, the first plays of life began. But this raises an even deeper question. If these primitive vesicles formed spontaneously, how did they evolve into the intricate membranes we see today, selectively permeable, laced with proteins, charged with electrochemical gradients? The short answer: time and failure. Most vesicles in the early Earth likely broke apart quickly. A bump, a change in pH, a rush of salt, any of these could tear apart their fragile walls. But some lasted longer. Maybe they stumbled upon a mineral-rich, tight pool that buffered the environment. Maybe they merged with other vesicles, swapping content, and gained a new layer of stability. Maybe one lucky vesicle surrounded not just random chemicals, but the right ones, the ones that could repair damage, or even replicate the membrane itself. These lucky vesicles didn't intend to survive, but they did, and from those survivors came more survivors. A quiet lineage, not yet alive, but slowly approaching the edge of life. Over countless years, membranes grew more robust. Fatty acid chains grew longer. Some vesicles absorbed cholesterol-like molecules, which added rigidity. Others, by sheer chance, trapped sequences of RNA that produced proteins, some of which embedded themselves into the membrane, strengthening it, or acting as gates. It's as if the vesicle began to recruit its own tools, modifying its walls not just for survival, but for function. Eventually, what had once been a simple lipid bubble became a complex, semi-permeable membrane, a gatekeeper that allowed some molecules in, pushed others out, and maintained the delicate chemistry within. This moment, the moment when membranes became selective, is one of the most critical turning points in life's story. Before this, chemistry was communal. The ocean was the lab. But after this, each cell became its own private world. The membrane marked a shift from chaos to order, from endless diffusion to internal planning. Now, cells could control their contents, regulate their energy, balance their ions. They could concentrate rare chemicals, maintain gradients, respond to stimuli. With this control came stability. With stability came complexity. And with complexity came the ability to evolve. And so, life crossed another threshold. It's almost poetic to consider that the first homes were not built with wood or stone, but with oil and water and time. They had no doors, no windows, yet they gave shelter to possibility. They allowed molecules to whisper to one another in protected spaces, to form bonds, to experiment in safety. And somewhere in one of these microscopic houses, the first heartbeat of life, soft, molecular, and unseen, began to stir. We might think of life as energy, as replication, or as movement. But perhaps life also begins with the idea of inside. and outside with the quiet decision of a molecule to draw a line between self and world. The membrane was that line, and even now, in every living cell across the planet, from amoeba to human, that ancient choice is remembered. Every cell carries the same kind of boundary. Every organism is still defined by a membrane, a soft, thin layer that says, "This is me." That is not, as you drift deeper into thought tonight. Consider this. Your skin, your blood vessels, your cellular walls, they all descend from those early vesicles, from the first time fatty acids curled into a bubble and offered sanctuary to the storm. You are, in a very real way, a walking memory of ancient chemistry, a descendant of shelter, the walls that surround you, your bones, your organs, even the thoughts that echo inside your mind began in a bubble, and the moment that bubble held tight against the current, the seed of life was planted. Now life had a home. Now it could begin to grow, far below the surface of the ancient earth, where sunlight never touched and silence reigned for eternity. There existed a place unlike anywhere else, a world of crushing pressure, eerie warmth, and chemical possibility. It was here, along the jagged scars of the ocean floor, that something astonishing began to stir, not in a single explosive moment, but gradually, almost imperceptibly. Over millions of years, these were the hydrothermal vents, towering mineral chimneys that spewed scalding water rich in hydrogen, methane, and iron. The temperatures oscillated wildly. The environment was toxic by most standards, and yet paradoxically, it may have been the cradle of life. Here, at the boundaries between scorching heat and icy seawater, lay a natural gradient, a difference in temperature, in chemistry, in energy, and perhaps most importantly, in potential. Nature loves gradients. Where there is imbalance, it finds a way to equalize, and in doing so, often stumbles into complexity. Imagine this ancient underworld. Black smoke as billowing plumes of mineral-rich steam into the cold, dark sea. Iron sulfide precipitating out in shimmering clouds. Microscopic pores in the vent walls, tiny, iron-lined compartments behaving much like the membranes of modern cells. They separated one chemical concentration from another, allowed molecules to collect and interact, shielded them from chaos just enough to let pattern emerge from randomness. This was no laboratory. There were no instructions, no architect, no guiding intelligence. But there was time, unfathomable stretches of it, and energy, constantly cycling. Molecules were broken down and built up again, over and over, in countless combinations. Some arrangements dissolved into nothing, but a few, just a few, may have endured. We often picture life beginning with something dramatic, a spark, a flash, a moment of sudden animation. But what if the true beginning was quieter? What if the first whispers of life were no more conscious than the tide, no more organized than a cloud of steam? What if life didn't begin in a place, but across a boundary, a blurry, shifting zone where the non-living gradually became the almost living? In those mineral pores, a dance began, one of carbon compounds and catalyzing metals, of proton gradients and electron shuttling. Primitive cycles emerged. Molecules that could replicate even imperfectly slowly began to outnumber those that couldn't. They weren't alive, not yet, but they persisted. And persistence in a hostile world was the first requirement. Over time, these early chemical systems may have developed something else. Cooperation. One set of molecules made conditions slightly better for another, and in turn, benefited from the other's presence. It was the beginning of synergy, a concept at the heart of biology. Not everything was competition. Sometimes survival meant alignment. You can almost picture it, a matrix of tiny compartments in the rock, each hosting a slightly different version of the same experiment. One may have favored heat-loving chains of amino acids, another spirals of primitive RNA-like strands. A third may have nurtured lipids, oily molecules that naturally formed spheres, mimicking the shape of future cell membranes. Each pocket a micro-laboratory, each with its own fate, and then, maybe just maybe, to systems combined. One that stored information and could replicate itself, and another that could harvest energy from the environment. This fusion, may have birthed the first protocell, not a living cell as we know it, but a boundary-wrapped container of possibility. It could grow, it could split, it could change, and most importantly, it could endure just long enough to do it again. What makes something alive? Is it replication, metabolism, a barrier between inside and out? Or is it something less tangible, the capacity to evolve, to adapt? If so, then perhaps the moment that truly mattered wasn't the first bubble of chemicals or the first reaction that released energy. It was the moment when change became inheritance, when a beneficial feature didn't just arise, but was passed on. This didn't happen all at once. There were surely millions of failures, systems that were unstable, structures that collapsed, sequences that couldn't hold on long enough. But in nature, failure isn't the opposite of success, it's part of the process. Evolution doesn't build perfection, it builds persistence. In time, the protocells became more complex. The chemical cycles inside them grew more robust. They started to capture energy more efficiently. They may have even begun rudimentary communication, a chemical whisper between neighbors. And then, one day, one of these simple containers, floating gently near a warm mineral vent, divided not because it was broken, but because it had grown too large, and both halves somehow retained the pattern that was not life as we know it, but it was a seed. A threshold crossed above these vents. The ocean remained dark. The surface world had no idea what was happening below. Volcanic storms raged across the continents. The atmosphere was still finding its shape. The moon, closer than it is now, pulled the tides like a great heartbeat. But below, unseen, unfelt, a lineage had begun. Billions of years later, that lineage would give rise to bacteria, to plants, to animals, to us. But we forget how humble that beginning was. Not a divine spark, not a perfect blueprint, but a lucky arrangement. A few stable cycles, a shelter from chaos. And time, after all, is nature's greatest experimenter. It does not rush, it does not judge. It simply tries everything again and again until something sticks. So perhaps life didn't begin in a single moment, but rather emerged like a shoreline in the fog, not suddenly appearing, but slowly becoming visible as conditions shifted. One molecule becoming two cooperating, a boundary forming, an inside, an outside, a before and an after, and in that deep, unseen world, in silence and heat and pressure, the line between the living and the not yet living blurred, then shifted, and something entirely new was born, not with a shout, but with a whisper. Before DNA was deciphered, before the structure of the double helix became a symbol of life itself, long before microscopes revealed the swirling complexity of cells, there was silence. And in that silence, something ancient whispered, not through sound, but through time, encoded in molecules that carried memory. You see, DNA is not just a chemical. It's a language written in an alphabet of 4 letters, A, T, G, and C, and hidden within its spiraling structure lies a map, not of a place, but of a history, a record of every trial, every accident, every spark that nudged life forward. If we follow that record backward, if we unwind the spirals of time encoded in every cell, we arrive not at a single creature, but at a common ancestor, a shadow at the root of life's family tree, one we've never seen, but one we can still feel, encoded in us all. This idea that all life is connected was once philosophical. Now it's scientific. It's called the last universal common ancestor, or LUCA for short. LUCA was not the first life. It was the life that left descendants. It was the organism from which all life on Earth descends: humans, trees, jellyfish, mushrooms, bacteria, everything. And though LUCA is long gone, its echoes remain, because the deeper scientists look into DNA across bacteria, across animals, across plants, the more they discover shared genes, genetic signatures that seem too precise to be random, fragments of ancient survival strategies passed from one form of life to another, like heirlooms in a family. So how do we find LUCA? Not through bones. It left no fossils, but through comparison. Scientists gather the DNA of many organisms from bacteria that live in boiling acid to fish in the deepest ocean trenches, and they line them up. They look for genes that are shared, not just similar, identical, preserved across billions of years. These genes act like ancient footprints, pressed into the whetstone of time before solidifying into molecular record, and what they've found is extraordinary. Luca likely lived over 3.5 to 4 billion years ago. It probably thrived in hydrothermal vent places where superheated water burst from Earth's crust, a landscape rich in minerals, heat, and chemistry. Luca wasn't a simple blob. It already had machinery. It could read RNA. It could build proteins. It could pass on instructions from one generation to the next. Imagine this for a moment. Somewhere deep in Earth's crust, in a vent no larger than a kitchen sink, tiny threads of molecules are replicating, reaching stability, and becoming heritage, not the kind passed through kingdoms or bloodlines, but through sequences of co-digital, wet living. This moment, this Luca, is not a thing we can point to. It's a convergence point, a narrowing of life's chaotic stream into a river that splits and branches, forming bacteria, then archaea, then us, and what's even stranger, Luca may not have lived alone. Some scientists believe Luca wasn't a single organism at all, but rather a community, a messy network of gene swapping, cell sharing, early organisms that over time consolidated into the biological language we now recognize as life. This idea is called the gene pool hypothesis. Imagine early life as an open market of parts. One organism discovers a useful enzyme, another borrows it. One learns how to metabolize sulfur. Its neighbor adopts the trick too. Instead of evolution happening in clean, tree-like branches, it was a swamp, a thick, tangled mat of collaboration, theft, accident, and genius. And then, out of that swamp, Luca emerged, not as the strongest, not as the most complex, but as the one whose toolkit for whatever reason persisted. That's the key. Luca didn't conquer the world. It didn't invent fire or flight or thought. It simply survived and left a trail of instructions behind. Instructions that echo in every cell that came after, including yours. Take a breath now. Feel your chest rise. Behind the breath, countless processes unfold: cell repair, protein synthesis, chemical signaling, all choreographed by blueprints millions of years old. Many of those blueprints trace back to Luca. You are not separate from ancient life. You are ancient life, rewritten, refined, reaching upward. The elegance of this idea lies in its humility. We often look up at the stars and ask, where did we come from? But maybe the better question is, who still lives within us? And when you trace life back to Luca, something changes in your perception. You realize life isn't a ladder. It's a web, and all strands trace back to the same root. You realize evolution isn't upward, or better, it's survival, adaptation, change, and you realize that your cells, right now, carry tools older than mountains, molecules that once swirled in steaming oceans when the moon was still young, and somehow, despite everything, they still work, sometimes in the quiet of night, when the world is still, and thought drifts like mist. You might feel something in your chest, a subtle flicker, a pulse, the same pulse that echoed in Luca's simple cell wall, unseen, unbroken, unfolding still. So here we are, billions of years later, still following instructions first written in shadows, still wondering where they came from, and where they'll lead. In the hush of prebiotic Earth, there was no heartbeat, no breath, no purpose, only the endless churn of elements, heat flickering from the crust, the sweep of tides under a pale sky, and gases swirling in a restless atmosphere. And yet, within that swirling chaos, something remarkable began to take shape. Order, not imposed from above, but coaxed from below slowly, delicately, like frost forming on a silent window pane. Imagine the early Earth not as a lifeless rock, but as a turbulent, chemical cauldron. Volcanic eruptions spewed gases like methane, ammonia, and water vapor into the atmosphere. Lightning sliced through storm clouds, delivering energy in jagged pulses. Meanwhile, in the shallow pools and undersea vents, minerals offered their surfaces as stages upon which atoms could dance. The entire world was a chemistry experiment, vast, unmonitored, and unfolding over eons. What emerged was not life, not yet, but something stranger, something halfway between lifeless and alive. Molecules that copied themselves, not with perfection, but with just enough consistency to keep going. These were not yet genes, but their shadowy ancestors, not yet cells, but proto-patterns, chains of amino acids, folded and fluttering, some by accident stable enough to last longer than others. This, scientists believe, is the origin of order, not imposed by an architect, but filtered through time. In the absence of consciousness, evolution began to operate not biological evolution, but chemical evolution. Molecules that lasted, endured, those that didn't, faded, over thousands, then millions of years. The environment acted like a sieve, letting only the most stable, the most reactive, the most strangely persistent forms accumulate. It's hard to picture. No eyes were watching, no plan was guiding. Yet, from this molecular chaos emerged cycles repeating chemical reactions that regenerated themselves. These cycles were like the first breaths of pattern, not alive, but foreshadowing life. Reactions that created their own ingredients, or converted simple compounds into complex ones, forming loops of self-sustaining chemistry. These loops didn't think, they didn't want, but they persisted. That, in itself, was enough. One such cycle may have involved fatty acids, which can form membranes in water. Tiny bubbles, simple spheres of fat, began to trap molecules inside them. These bubbles acted like primitive containers, not alive, but suddenly capable of holding together the ingredients of life in one place. Now, chemical reactions that, once diffused away, could occur in closer quarters. Concentration increased, interactions intensified. The chemistry of randomness began, slowly, to feel less random. What's striking is that this progression from molecules to self-replicating chains to reaction loops to bubbles all happened before anything could be called alive. There were no cells, no DNA, no purpose, just molecules reacting to their surroundings, shaped by heat and pressure and chance. But across the entire planet, these micro-experiments were happening in parallel. Millions of tiny tests running every second for millions of years. The numbers are staggering. Imagine a single droplet of early ocean water. It contains trillions of molecules, each colliding, bonding, breaking apart. Then imagine that across every tide pool, every hydrothermal vent, every crevice and crack where minerals bubbled up from the deep earth, these collisions were happening endlessly. It's like rolling dice, not once, but 1 trillion times per second across the entire planet for 1 billion years. Eventually, some rules were bound to land just right, and when they did, those configurations didn't vanish. They lingered. They influenced nearby molecules. They changed the local chemistry in ways that helped themselves survive. That, right there, is the first whisper of what we now call metabolism, not yet a living process, but a process that favored stability and structure. We often imagine life beginning with a single lucky accident, a spark, a bolt, but the truth might be slower, gentler. Life may have crept in, not exploded. It may have arisen not from a miracle moment, but from a slow drift toward complexity, a tide, not a leap. Consider this. Molecules that formed stable loops had a slight advantage. They regenerated themselves. Then those loops got trapped inside fatty bubbles, which kept them from washing away. Over time, the bubble and the loop began to rely on each other. A new kind of relationship emerged, one where chemical parts worked better together than apart. This is the root of cooperation, and perhaps the first hint of something that could grow. From this mingling, complexity blossomed. Some loops evolved into primitive metabolic pathways. Others became information carries, the ancestors of RNA, which could both store information and catalyze reactions. These dual-purpose molecules were game changers. They could copy themselves not with complete fidelity, but close enough. Occasionally, an error in copying would create a new variant, some better, some worse. For the first time in Earth's history, Evolution by natural selection had something to work with. What came next was not inevitable, but it was increasingly likely. The loops became networks. The bubbles became containers. RNA strands became templates. The chemical soup became a laboratory for feedback, cooperation, error, and correction. The chemistry of life began to refine itself, and as the centuries passed, something uncanny took root. These systems, once scattered and spontaneous, began to converge into something resembling life. Self-sustaining, self-replicating, adaptable. It wasn't alive as we know it. But it was no longer merely chemistry. It was protocells. These protocells were not truly living, but they were close. Each one a fragile shell of fatty acids, enclosing loops of RNA or other catalytic molecules, capable of growing, copying, and even on rare occasions splitting. Those that did this well survived longer. Those that didn't dissolved. The planet by then had become an enormous testing ground, and protocells were the first runners in the race of life. Some may have drifted to the ocean floor, others boiled near volcanic vents. Some floated in shallow pools under sun and storm. They were not smart. They had no minds, but they were persistent. And persistence in a world ruled by change is everything. Eventually, one of these protocells got lucky. It copied itself just a bit better, held its shape just a bit longer, managed to string together just the right sequence of reactions to survive where others couldn't. That cell, anonymous and alone in the vastness of PI life Earth, was the ancestor of everything that followed. Every whale, every tree, every breath, every thought, all of it began with that single cell, and the billion-year journey that led to it. A journey not guided by design, but shaped by the silent logic of chemistry and time. So when you look in the mirror, or up at the stars, remember, you are made of atoms that once danced in chaos, and slowly, over uncountable years, found a rhythm. You are not a miracle. You are something rarer, inevitable. For a long time, we've believed that DNA is the very foundation of life, that without genes, without that double helix coiled like a microscopic scroll, life could not be. But what if we turn the lens even further back to a moment in time where life may have flickered without a genome at all? It's strange to imagine, isn't it? A world where nothing carries instructions, where no blueprint has yet been written, and yet, somehow, processes still unfold. Something still moves, something still changes, something almost learns to replicate. In this chapter, we step into that in-between state, that delicate hush in Earth's deep timeline, where chemical chaos flirts with biological intention, and the idea of life is still a suggestion, not yet written in nucleotides or genes. Let's begin. In silence, long before DNA and RNA, before cells wrapped themselves in lipid skeins and whispered across time, there were molecules. Billions of them tumbling and tangling in Earth's primordial stew. Some simple, some more complex. Some reacting by accident, others reacting by chance so consistently it almost looked like intention. There's a concept in prebiotic chemistry known as autocatalysis. It's a big word, but a simple idea. A molecule that helps produce another molecule, which then helps produce more of the first. It's like a loop, a cycle, a whisper between matter and time. I will help make you, if you help make me, in a universe with no language, no purpose, no goals. That small agreement between molecules is enormous. It's not quite life, but it's not quite non-life either. These autocatalytic cycles could replicate themselves in a crude sense. They didn't need a code. They didn't need DNA to spell out instructions. Their structure alone was enough to keep the dance going. If a molecule helped others appear, and those others helped it return again, then the cycle became more than chemical. It became persistent. That's the first taste of survival. Not conscious, not planned, but a kind of chemistry that lasts, while other reactions fade away. Scientists call this the metabolism first theory. It suggests that before life had genes, it had systems, not blueprints, but functions, self-sustaining chemical networks like tiny metabolic storms forming, dissolving, reforming again in shallow pores, near volcanic vents, or beneath icy crusts, and in those networks, the groundwork of biology was being laid, not with words, but with action, not with instructions, but with repetition. Imagine a set of molecules, ones that just happen to lock together into a loop of reactions. One reaction leads to the next, then the next, until miraculously it cycles back to the beginning. Like a snake eating its tail, every time the loop completes, it makes more of itself, more of its components, more of the conditions it needs. It reshapes its environment slightly, just enough to make itself easier to exist. That's the essence of primitive metabolism, and perhaps the first whisper of natural selection. Now picture this cycle happening not in isolation, but inside. A bubble, a lipid vesicle, a fatty droplet formed when certain molecules cluster in water. These bubbles don't need DNA to form. They happen naturally when conditions are right. They can even grow and split and grow again. So now you have a chemical loop inside a chemical container, something that maintains a border between inside and out, something that defines a little world of its own. Is that life? Not quite, but it's close. So close. This moment in Earth's story where function precedes code is one of the most mysterious, because it challenges everything we thought life needed. We always imagined DNA as the spark, but what if DNA came after the spark? What if the first forms of life were systems, not scrolls? This flips the narrative. Instead of thinking, what wrote the instructions, we start asking what behaviors were already working before instructions were even necessary. That's what metabolism first theories suggest. That function came before description, that Earth didn't need a language before it had action, that living systems learned to do before they learned to document. Let's pause and imagine that timeline visually. Close your eyes for a moment and stretch the story out before you. On one end, you have pure chemistry, raw reactions. Energy flows, molecules forming and breaking apart like raindrops on hot stone. On the other end, you have complex cells, genomes, membranes, organelles, survival mechanisms, and communication signals. Somewhere in the middle sits this strange, humming silence.no genes. No memories, only patterns that repeat, cycles that stabilize, structures that persist without needing to know they are persisting. It's the era of polygenomic life, the era before recording, the era of doing, not saying. Now, eventually, this chemical dance needed something more. It needed a way to store its progress, to remember the reactions that worked, and the ones that didn't, to pass on successful patterns not just by luck, but by mechanism. And that's where the next chapter of life begins, with RNA, and eventually DNA, with molecules that don't just react, but also replicate themselves, with high fidelity and useful variation. But we're not there yet. Right now, we sit in the hush. Right now, we're in the final breaths of a world where life flows without rules, where nothing is written down, where everything is felt, not told, reinforced through time, not memory. It's like trying to recall a dream that never happened, a feeling of familiarity with no details to back it up. Modern science is just beginning to map these polygenomic systems. Some researchers build artificial chemical loops in labs, watching them self-sustain and even adapt under changing conditions. Others simulate protocells with no DNA, just lipid containers and metabolic functions that rise and fall like early weather. The goal is simple but profound, to show that life doesn't need a blueprint to begin. It only needs persistence and context and time, with enough cycles, enough stability, and just enough boundary. Even a mindless molecule can seem to choose to survive, and once that illusion of choice takes root, it's not long before memory follows. In the great story of Earth, this is the chapter most forgotten, the time before memory, before language, before inheritance. It is a time of quiet genius where the only rule was, if it works, let it happen again. As we drift back from this forgotten silence, we carry with us a deeper understanding that life is not a sudden spark. It is a long and quiet burn, and before the code was ever written, the fire had already begun. The story of life long entangled in the shallow pools and volcanic margins of the early Earth, had been an epic of endurance. For nearly 2 billion years, life clung to simplicity tiny, single-celled beings drifting through ancient oceans, feeding on sunlight or minerals, dividing slowly, leaving behind whispers in stone. And then something stirred, something changed, not quickly, not explosively, but gradually, over countless millions of years. Complexity began to take root. It did not start with animals, or plants, or anything with eyes or limbs. The true leap, the one that opened the doors to all that would follow, was the emergence of the eukaryote in today's terms. Eukaryotes are organisms whose cells contain a nucleus, an internal command center wrapped in its own membrane. This alone might not sound dramatic, but to understand its significance, you must first imagine a world dominated entirely by simpler creatures, prokaryotes, like bacteria and archaea, whose internal structure was bare and open. Everything mingled together in the soup of the cell. The DNA, the enzymes, the proteins, all floating loosely, unseparated. But one day, somewhere in an ancient warm sea, perhaps near a volcanic vent, or a shallow lagoon, a prokaryotic cell engulfed another. This might have been an act of attempted digestion, or a failed act of defense. But the engulfed cell wasn't broken down. Instead, it survived, and eventually began to live inside its host. This was the endosymbiotic event, a moment so rare and strange that it may have happened only once in the entire history of life. The engulfed cell became mitochondria, the energy-producing engine of every complex cell on Earth today. And with this energy surplus, something unimaginable became possible. A greater architecture, a new kind of cell, a platform for complexity. From this union, eukaryotic cells were born, cells with compartments, organization, and most importantly, potential. These new cells were like small cities, with specialized roles, transportation, channels, and power plants. They were more adaptable, more robust, and with the right environmental pressures, they could begin to cooperate. Life no longer had to rely solely on the power of one. The next chapter was about unity. This gave rise to the multicellular revolution. It sounds poetic, perhaps even obvious to us now, but the idea that individual cells could work together permanently as part of a greater whole, that they could sacrifice their autonomy for shared survival, was no small feat. At first, it might have been little more than loose clusters, maybe 2 or 3 cells stuck together after division. Perhaps they found safety in numbers. Perhaps they absorbed nutrients more efficiently as a group. Whatever the initial advantage, it was enough, and soon, across the oceans, something new began to take shape. Cells began to specialize. Some became better at absorbing nutrients. Others focused on movement. Some began to detect light. Over millions of years, this division of labor would create the blueprint for every creature we know. Plants with leaves, animals with muscles and nerves, fungi with sprawling threads. But it started as nothing more than a simple colony or sheet of cells floating through shallow seas, dividing and diversifying, slowly learning how to share. One of the earliest known examples is a tiny creature called Grippania spiralis, a coiled fossil found in rocks over 1.5 billion years old. It may have been one of the first multicellular algae, barely a few centimeters long, but its shape suggested structure, pattern, an early whisper of form. For hundreds of millions of years, life experimented. Most multicellular organisms were still tiny, soft-bodied, and fragile, leaving behind almost no trace. But beneath the surface, the rules were being rewritten. Evolution, always slow but relentless, was preparing for a new phase. Then came the Ediacaran period, around 600 million years ago, a strange and beautiful time, when the seafloor became a canvas for life's earliest large-scale artwork. The creatures of this era were alien to us, flat, frond-like beings with no clear head or tail, no mouth or limbs, just rippling patterns and soft bodies pressed into ancient mud. Some grew meters long, yet left no descendants we can trace. They may have been evolutionary experiments, unsuccessful, some lost to time, But the idea of large multicellular bodies had taken hold. Life had begun to move beyond the microscopic. Complexity was no longer an anomaly, it was becoming the norm. And then, perhaps the most dramatic event in the history of biology, the Cambrian explosion, around 540 million years ago, in what feels like the blink of an eye in geological terms. The fossil record explodes with diversity. Creatures with shells, legs, eyes, jaws, and even brains emerge in rapid succession. The first arthropods, early worms, strange forms like Lycopodium with 5 eyes and backward-facing mouths. These were not shadows in rock, but clear, definable beings. Some darted across the seabed, others floated and hunted. Some dug into the sand. Life had burst into complexity with dazzling speed. What caused this sudden leap is still debated. Perhaps oxygen levels rose just enough to allow for larger, more active animals. Perhaps predator-prey relationships ignited an arms race. Maybe genetic mechanisms like the development of Hox genes, which control body plans, allowed for a surge in variety, whatever the cause. This was the moment when animal life truly began. It is important to understand that this leap from single cells to complex organisms did not erase the simpler forms. Bacteria and archaea still thrived, as they always had, but now they shared the planet with beings that had muscles, eyes, nerves, and intentions, beings that could crawl, sense, and eventually think. The ocean became a theater of motion and interaction. Burrows appeared in sediment, for the first time evidence of creatures that could move with purpose. Predators carved out niches. Coral-like creatures built early reefs. For the first time, ecosystems formed complex webs of interaction, symbiosis, and struggle, and all of it every eye, every limb, every organ traced back to that improbable fusion between 2 cells over 1 billion years earlier. A moment of cooperation, of absorption without destruction. A moment that changed everything. As the Cambrian Sea shimmered with life, the stage was now set for the next grand act, colonizing the land, transforming barren continents into green kingdoms, and bringing the story of life ever closer to us. But that journey, the crawl from water to earth, from fins to feet, awaits us in the next chapter. In the primordial chaos, long before words were ever spoken, and before the human tongue had anything to say, Earth was already humming with a subtle rhythm, one not of speech, but of molecular exchange, of repetition, of chemical motifs, echoes of what could someday become a kind of proto-language. Not language as we understand it with sounds and symbols, but structure, signaling, code, and long before minds could comprehend. These whisperings of early biology hinted at something remarkable, a transition from blind chemical spontaneity to regulated communication within life. And in this chapter, we walk into the slow unfolding of this strange music of matter, how molecules began to speak to each other in structured sequences, how these whispers laid the foundation for the first genetic blueprints, and how, somewhere, in the deep past, a kind of molecular grammar was born. Let us drift backward once more into the warm, mineral-rich pools and chaotic shorelines of PI life Earth. At first, everything was still clumsy, accidental. Fatty acids collided and formed unstable membranes. Strands of RNA copied themselves in error-prone loops, breaking and reforming as tides rose and fell. Nothing held permanence. But amidst this instability, patterns emerged not from will, but from physics, from geometry, from chemistry's silent constraints. Certain molecules began to prefer one another, one amino acid bent toward another, not randomly, but in predictable angles, small hinges forming from the way atoms repelled or attracted, forming folds, curls, and spirals. These were not yet proteins, but they were gestures, small, repeating structural units, beta sheets. Alpha helices arose again and again, like the first syllables in a molecular chart. Meanwhile, the strange world of nucleotides, the A's, U's, G's, and C's of the RNA world became more disciplined. Chains of bases stopped being only sequences and started becoming signals. A certain combination at the beginning of an RNA strand increased the likelihood that it would be recognized by nearby catalytic surfaces. Another combination stabilized the strand itself from being torn apart by surrounding ions. It was as if chemistry was accidentally discovering punctuation. One sequence of bases told a ribosome, "Start copying here." Another marked the end. These weren't conscious markers, but they worked, and over time, the molecules that used these subtle codes survived longer, made more copies, persisted while the rest dissolved into forgetfulness, and so proto-syntax emerged. Imagine a strand of RNA with not only a code for catalysis, but also a segment that allowed it to fold into a tiny claw, a shape that could bind another molecule, even bring two reactants close enough to touch. The RNA wasn't just carrying information anymore, it was performing functions. Like a sentence in a strange biochemical language, each region had meaning, structure, even intent, though no mind yet existed to hold it. Now let us imagine a pool shallow, warm, dense with ions and sediment. In this pool, trillions of molecules jostle for attention, most falling apart. But a few possess an uncanny order. Their sequences allow them to fold with precision to survive the buffeting heat. One recognizes a short chain of amino acids floating by and links it to another. Another catalyzes a reaction that helps lipids form bubbles around themselves, like a kind of primitive cell wall. These sequences are not arbitrary. They are the survivors. They're the ones that followed the unspoken rules of this new language. Rules carved not in intention, but in mathematical stability. Certain folds took less energy. Certain sequences bent at perfect angles. Nature wasn't rewarding poetry, it was rewarding efficiency. Yet from that, a kind of grammar was born. A grammar of persistence. Over time, the surviving sequences became more complex. Multiple regions folded into multi-domain structures. Some strands of RNA folded into loops that acted like switches, turning catalytic activity on or off depending on what molecule was bound nearby. These were primitive feedback systems. We might now call them regulatory motifs. And though they were not yet alive, they foreshadowed how life would someday regulate itself, internally aware, responsive, self-adjusting. Here, in these quiet folds and bonds, the difference between just chemistry and early communication begins to blur. Because what is language, if not a system that takes symbols and gives them function? In our cells today, this echoes forward in stunning clarity. DNA is just a string of symbols, letters written in a chemical script. But what gives those symbols meaning is the machinery that reads them. The ribosomes that translate, the polymerases that scan, the proteins that bind to specific promoters, enhancers, silencers. This machinery is the evolved child of those first molecular whispers. In those ancient pools, the machinery was just beginning. Perhaps it started with RNA molecules that folded in a way that attracted metal ions, magnesium or iron, allowing them to hold their structure longer. Or maybe certain ribosomes discovered, through random variation, that specific sequences acted like control levers. Binding one molecule changed their shape entirely, like a key turning in a lock. Now they could turn on only when the right molecule was present. That's not far from how our neurons now work. Fast forward billions of years, and human brains echo the same logic. Electrical signals turned on or off based on receptor bindings. Synapses strengthening through use. Proteins folding based on upstream triggers. At the base of it all, sequences, structures, response. The language of molecules, scaled upward, growing more elaborate, more self-aware. Back in the ancient pools, a new transformation was brewing. Imagine multiple strands of RNA, each with different functions, one that catalyzed reactions, another that helped build lipid walls, another that stabilized pH by binding hydrogen ions. What if these sequences began to associate together, not randomly, but in symbiotic clusters? They coexisted better than alone. Some scientists have proposed hypercycles, systems where multiple catalytic RNAs supported one another in closed feedback loops. A primitive mutualism. Here, the beginnings of context emerged. One sequence's meaning depended on the presence of another. The language was becoming relational, not just code in isolation, but instructions contingent on the entire system state. It wasn't quite sentience, but it was awareness in the chemical sense. The system knew what it was doing, because its survival required memory, response, and adjustment. In today's biology, this echoes in gene regulation networks. Some genes are only expressed if others are silenced. Some proteins require CO factors to function. Entire feedback loops maintain homeostasis, but it all began with these soft echoes. In the ancient mud, one strand turning on another, which in turn silenced a third. Molecular cause and effect. Whispered sentences in the language of life. As we draw this chapter to a close, consider the breathtaking paradox. The earth, in its earliest days, was loud with silence. There were no voices, no eyes to see, no ears to hear. And yet, under the surface of that quiet, a dialogue was taking place. Molecules bending to one another, learning from each other's presence, adapting through structure. Information was not yet written, but it was spoken in folds, in loops, in catalytic turns. These were the whispers of syntax before speech, the grammar of persistence before intention, the language of life before there was life to speak it. And so, the first conversations on Earth were not human. They were not even animal. They were small molecular interactions, repeated millions of times, honed by heat and chaos and time into something structured, something meaningful, something that one day would become a voice. In the relentless rhythm of Earth's history, there exists a curious paradox. The gentlest seeds of life may have flourished not in calm, fertile plains or crystal-clear pools, but rather in the most violent and inhospitable corners of the young planet. Scorching volcanic fields, deep-sea hydrothermal vents, acidic lakes, freezing deserts, and salt-encrusted basins, places where no human life could survive for even moments. These are the locations where early life not only emerged, but learned to persist, adapt, and eventually evolve into everything that followed. We now venture into these extreme habitats not in search of destruction, but to understand how struggle and chaos served as the cradle of life's earliest endurance. The Earth, at the time when microbial life was beginning to take hold, was a turbulent sphere of energy and flux. Oxygen was scarce, ultraviolet radiation was brutal, and tectonic upheaval reshaped the land and sea in cycles of creation and collapse. Yet, within these violent forces lay unique opportunities. Chemical gradients, mineral-rich fluids, electrical currents, and heat differentials, all of which provided energetic scaffolding for life's improbable genesis. Let us begin our exploration at the bottom of the sea, where ancient black smokeless towering vents of superheated water still roar to this day. These vents spew scalding fluids, enriched with metals and sulfides, into the icy darkness of the deep ocean. The temperature of their mouths can exceed 4°C, and the surrounding pressure is crushing. Yet remarkably, in these places, scientists have discovered rich communities of extremophiles organisms that not only tolerate but depend on these extremes for survival. One group of such organisms is the thermophilic archaea, ancient microbes that thrive at high temperatures. Some of these archaea are chemolithotrophic, meaning they draw energy not from sunlight, like plants, but from inorganic chemical reactions. They feed on hydrogen sulfide and iron, using enzymes uniquely equipped to perform life-sustaining tasks under high heat. It is here, many researchers propose, that life may have first learned to feed itself not with light, but with the deep breath of the Earth's crust. This possibility leads to a provocative idea, that life began not at the surface, but in the subterranean shadows. Far from the sterilizing rays of the young sun, the early Earth's surface was bombarded by meteors and UV radiation, but in the hidden crevices of oceanic crust, shielded from the worst of these cosmic assaults, microbes could persist. These dark, mineral-rich environments offered stability, chemical energy, and a structure within which self-replicating molecules could assemble and endure. But the story does not end in darkness. Elsewhere on the surface of the planet, other extremophiles were engaged in their own battles for existence. In boiling springs and acidic lakes, microbes called acidophils and halophiles were learning to endure pH levels and salinities that would instantly destroy more fragile forms of life. They evolved sophisticated pumps, protective coatings, and unique metabolic pathways to protect themselves from their surroundings in frozen environments, such as the polar regions and high mountaintops. Psychrophiles, cold-loving microbes managed to stay active at sub-zero temperatures. Their cell membranes were flexible, and their proteins worked even in conditions that would freeze water into solid ice. They taught us that life does not need warmth to exist, it only needs the ability to adapt. Everywhere we look, Earth's extremes seem less like obstacles and more like testing grounds. These environments are not fringe cases, but central chapters in life's early education. They represent the boundaries of possibility, stretched further with each evolutionary leap. One of the most intriguing discoveries in recent decades was the realization that DNA and proteins, our central molecules of life, are not well suited to extremes on their own. What keeps them intact in such places are small helper molecules, like chaperonins and compatible solutes. These chemical assistants act as shields, stabilizing the delicate machinery of life, even as temperatures swing wildly or acidity reaches dangerous levels. It is almost as if life learned to carry its own fortress, molecule by molecule. These adaptations did not arise in a single moment, nor from a single cell. They were learned over billions of years, passed down and improved generation after generation. The extreme habitats where they formed acted as evolutionary crucibles, harsh filters that allowed only the most resilient traits to survive. As these traits accumulated, organisms became more complex, more diverse, and more capable of venturing into new, less extreme realms. Eventually, life began pushing back toward the surface, toward the light. Some microbes, previously reliant on sulfur and iron, began harnessing photons from the sun. This shift gave rise to the first photosynthetic organisms, such as cyanobacteria, which would ultimately alter the very chemistry of the planet by releasing oxygen into the atmosphere, a development that would both empower new life and extinguish others. But even after the oxygenation of Earth, extremophiles did not disappear. They continued to thrive in isolated corners of the planet, and they remain with us today, silent witnesses to our shared ancient past. They live in the geysers of Yellowstone, the briny lakes of Antarctica, the crust of deep rocks, and even in nuclear reactors, an echo of the environments that molded their ancestors. To understand extremophiles is to understand resilience. Life did not emerge in a paradise, it emerged in fire and ice, acid and darkness, under crushing pressure and amid volcanic storms. It was shaped by adversity and sculpted by endurance. These organisms remind us that life's primary instinct is not to thrive, it is to persist, to exist in whatever form it must, wherever conditions allow the faintest whisper of chemistry to stir into structure. And so we must ask, if life can emerge and persist in such environments on Earth, might it not also exist elsewhere, beyond our planet, in the shadows of Mars, or beneath the icy crust of Europa or Enceladus? Our study of Earth's extremophiles has fundamentally shifted how we approach the search for extraterrestrial life. We no longer seek blue skies and green forests, we seek hydrothermal vents, frozen oceans, salt plains, and volcanic scars. The story of extremophiles is a reminder that we are not alone in our fragility. We carry their legacy in our DNA. The same enzymes, the same stress responses, the same molecular defenses that keep extremophiles alive in boiling acid are present, in modified form, within us. They are our ancestors' small, strange, and fierce thought in these ancient, hostile places. Life learned not only to survive, but to adapt, to grow, to explore, and eventually to dream. And in doing so, it set the stage for every living thing that would follow. Even now, when you close your eyes and picture the beginning of life, Imagine not a tranquil paradise, but a world of roaring fire, electric storms, and endless ice. In those moments of pure survival, the seeds of all future life were sown, and from those seeds, a universe of possibility was born. Far beneath the surface of Earth's ancient oceans, in waters untouched by sunlight, a revolution was stirring. It didn't roar, it didn't thunder. It whispered in the slow rhythm of tides and the patient drift of plankton. The world was quietly shifting from simplicity to sublime complexity. We had witnessed the slow evolution of single-celled organisms, the formation of basic multicellular bodies, the birth of photosynthesis and oxygen, and now life was preparing for its boldest leap yet, into the symphony of ecosystems. In the darkness of the deep, where light never reached, life had learned to thrive in shadows. Bacterial mats, colonies of archaea, and strange chemotraphs had been feeding of the Earth's inner heat for billions of years. But something had changed. A critical mass had been reached. A threshold had been crossed, and slowly, from the ocean floor, tiny, soft-bodied creatures began to appear. They left no bones, no shells, only faint impressions in ancient sediment. But these impressions tell us a remarkable story. This was the Ediacaran period, a mysterious and elusive time in the fossil record, roughly 600 million years ago. And it marked the beginning of Earth's first real ecosystems. Imagine a seabed bathed in filtered blue darkness, carpeted with waving fronds, flat, quilted discs, some shaped like leaves, others like spirals. They had no eyes, no mouths, no clear nervous systems, and yet they were alive, and they were not a lone dot in this alien seascape. Some creatures stayed rooted in place, absorbing nutrients directly from the water. Others floated. Some crawled slowly across the muddy floor, and a few, just a few, might have even grazed or preyed upon their neighbors. It was a quiet kind of complexity, not the teeth and claws we'd see later, but a gentle web of interdependence. For the first time in Earth's history, life wasn't just existing, it was interacting, shaping the environment, and being shaped in return. This was the birth of ecological roles: producers, consumers, decomposers, the earliest hints of food chains, of balance and imbalance. And it didn't stop at the ocean floor. Higher in the water column, tiny organisms, zooplankton and phytoplankton, began to flourish in vast numbers. Microscopic, but mighty, these drifting creatures became the lungs and larder of the ocean. They turned sunlight into sugars. They fed the growing communities below, and in doing so, they transformed the sea itself into a living, breathing system. Currents carried nutrients. Tides transported larvae. Entire coastlines became breeding grounds. The oceans were no longer just a habitat. They were becoming an engine of complexity. Over time, this slow bloom of biodiversity gained momentum. Some organisms began to experiment with symmetry: 3 arms, 5 arms, radial and bilateral designs. Some found success by flattening out, others by curling up, and some began building shells, hard parts. For the first time in billions of years, life began to protect itself, not with hiding or floating or fusing into mats, but with armor: calcium, carbonate, silica, chitin, minute defensive structures at first. But it was only the beginning, because something was coming, something extraordinary. The oceans were about to explode with innovation. But for now, in this chapter, we linger in the hush before the storm. In the Ediacaran twilight, scientists still debate what many of these ancient forms were. Were they animals? A strange offshoot, something entirely alien to the modern tree of life. Many disappeared without a trace. Others left hints that would be picked up millions of years later. But one thing is clear: this was a turning point from isolated survival to cooperative living, from single functions to distributed networks, from simplicity to ecosystems. It's hard to describe the feeling of standing before an Ediacaran fossil. A simple impression, barely more than a shadow in stone. And yet, it whispers of the first cities of life, built in silence, deep in the ocean's cradle, a garden without sunlight, a beginning without an end. Even now, we know so little. The deep keeps its secrets well. The soft bodies of Ediacaran creatures rarely fossilized, and most of what they created is long gone. But the idea they gave birth to, of interconnectedness, of function, of flow, would go on to define all life that followed. Without them, there would be no food webs, no forests, no herds, no coral reefs or kelp forests or mangrove jungles. The rise of marine ecosystems was more than a change in biology, it was the beginning of community. And community is what allows life to thrive, to adapt, to persist. As we drift through this ancient ocean, let us honor the silent architects of interaction, the soft-bodied pioneers who taught life how to live together. They never roared, they never hunted, they never built pyramids or cities, but they made the world ready for all that would come next. Close your eyes and imagine this, somewhere, not too long after the earth had cooled, under the blanket of a violet sky tinged by volcanic gases, something improbable was quietly stirring on the edge of a geothermal pool, within the cracks of basalt rock, in droplets suspended on clay surfaces, or perhaps in the evaporating edge of a tide pool. Molecules were dancing, not in a waltz rehearsed or guided, but in chaos, in beautiful, irrepressible chaos, each motion unplanned, each connection uncertain. Yet, from this field of randomness would come the seeds of intention. It was here, in these unlikely crucibles, that chemistry began its most rebellious act, becoming biology. At the heart of this transformation was a kind of symmetry, and also an asymmetry, for life at its roots is obsessed with breaking perfect balance. It thrives not in stillness, but in gradients of heat, of light, of molecules, of meaning. The lipids formed bubbles, self-contained spheres, membranes. Within these bubbles, strands of primitive RNA formed spontaneously, not as grand plans, but as accidents. And yet, these accidents began to repeat themselves. Some survived the next wave, the next burst of heat. Others did not. The Earth was their judge, and the Earth played no favorites. Imagine molecules drifting in and out of those early proto-cells, bringing with them energy, or information, or just the hint of a new reaction. It is here we find a strange kind of intelligence, not in neurons, not in thoughts, but in probabilities. If a sequence helped a bubble replicate faster, it survived. If it consumed energy more efficiently, it lingered. Evolution didn't wait for animals. It began at the molecular level. But let's drift a little deeper into the mystery of replication. Some of the earliest strands of RNA could make rough copies of themselves. Not perfect ones, not even consistent ones, but each copied form had the mere chance to be something more. And in this chance, life leaned forward. A single nucleotide changed. A slightly faster fold emerged. A new possibility was born. And from this strange feedback loop, a silent momentum grew. You might imagine that such a system is too fragile to last, that bubbles of fat and fragile strands could be blown apart by the faintest wind or smallest spark. And yet, it is in this fragility that resilience was born. The system adapted, or more accurately, the systems that didn't adapt vanished. The ones that remained were survivors of a brutal, mindless lottery. Now, zoom out for a moment. The planet, once molten, was cooling. Oceans were swelling, storms were raging, lightning still cracked across the sky, igniting new chemical reactions in the atmosphere. Every flash, every drop of rain, every gust of wind was a dice roll, spinning the molecular wheel over and over again. Most combinations meant nothing. Some formed toxic soups, others pure stasis. But once in a great while, in one invisible speck of water on one humble rock, the elements came together in just the right way, and life didn't just form once. It lightly sparked, fizzled, and sparked again countless times before something stable took hold. Before the probabilities started favoring persistence over randomness, there's a kind of elegance in this idea that consciousness, intelligence, awareness, all of it began as a random chemical game played by a blind universe with no audience. And yet, in time, that game would create the audience itself. But what makes this even stranger is what came next. The RNA world, as scientists call it, didn't last forever. RNA was clever, it could store information and catalyze reactions, but it was fragile. DNA would take over the job of long-term memory. Proteins would eventually become the workhorses of the cell, doing complex chemistry with infinite variety. But the transition didn't happen overnight. There were likely hybrid cells, halfway between RNA and DNA worlds. Some primitive molecules trying out new strategies for survival. There were mutations, many of them lethal. There were sequences lost forever. But each failure sharpened the blade of evolution, honing the molecular machinery of survival. And from this slow, painful grinding process arose Luca, the last universal common ancestor. Luca wasn't the first life form, but it is the one that left descendants. Every bacterium, every tree, every bird, every human is an echo of Luca. She, if we are to anthropomorphize, was not a queen or a conqueror, but merely the lucky one. The one whose code endured, the one who passed her blueprint forward. Now, let's pause here, because in this tale of probability and chemistry, of chaos and feedback, there's something strangely poetic. Life didn't begin with intention. It wasn't willed into being. It was stumbled into. It was a side effect of physical laws acting on a very specific range of conditions. And yet, once the door was opened, once even the smallest loop of replication was formed, evolution walked through it like a shadow. Every advancement from that point forward, metabolism, respiration, photosynthesis, was not a sudden leap, but a slow ripple, a gradual tightening of order in a universe tending toward disorder. Entropy may be king in physics, but in the pockets where energy flows like around hydrothermal vents or sunlit pools, complexity can take root, even if only briefly. And sometimes brief is long enough. Life is the great exception, the strange song that plays in a theater of silence, and its first notes were dissonant, fragile and clumsy. But even dissonant notes can form symphonies, given enough time. So, tonight, as you let your thoughts float into the quiet tide of sleep, picture this: a young earth, storming and restless, brimming with hidden potential. Picture bubbles forming, breaking, forming again, strands of molecular code tangling like ribbons in invisible currents. No eyes to see, no hands to shape, just chance playing with the puzzle of complexity. And somehow, from this swirling dance of uncertainty, came life, not just once, but again and again, until the conditions were just right, until one replication gave birth to another, and then another, until chemistry, against all odds, began to remember, began to grow, began to become. And so, the great inheritance began, one chain, one loop, one imperfect copy at a time. Sleep now, and know that your very existence is part of that first story, a story not of perfection, but of persistence. Somewhere along the winding corridors of time, in the flickering half-light of a planet still sculpting itself, a question began to form, not in words, nor in symbols, but in sensation, in tiny pulses of interaction, in chemical dialogues, passed from one primitive neuron to another, a question so faint and buried in biochemical murmurings that it would take billions of years to emerge fully. What am I? This is the chapter of emergence, of awareness, of the first fragile sparks, of what we now call consciousness. Close your eyes and imagine the Earth at a time when the oceans had already become nurseries of complexity, where cells had evolved into colonies, colonies into systems, and systems into organisms with eyes, limbs, and instincts. These were not random blobs anymore. They could swim, crawl, flee, and chase. They responded to heat and cold, to pain and pleasure, to hunger and safety. But responding was not yet reflecting. Instinct was not yet introspection. So, how did it begin? We often think of consciousness as something sudden, a switch flipped, a soul dropped from the heavens, a lightning strike awakening the mind. But nature rarely deals in sharp lines. More often, she whispers gradients, one molecule at a time, one adaptation at a time, one neural knot giving way to another. And over millions of years, something emerged that wasn't just reacting, it was observing its reactions. Let's walk back to the earliest nervous systems: jellyfish, flatworms, creatures that had the first crude networks of neurons, simple cables conducting impulses from the outer skin to muscle or mouth. These neural nets had no brain, no center. They were decentralized webs of feeling, but they were enough to create coordination, enough to create behavior. The flatworm, for example, could move toward light or away from it. It could decide, in its own limited way. That decision came from the integration of signals, sensory input combining with past chemical states to guide movement. Was this consciousness? No, but it was proto-consciousness. The scaffolding. Then came the ganglia clusters of nerve cells, tiny command centers. With these came more complex responses, feedback loops, conditional behaviors. And then, in some early ancestor of the arthropods or mollusks, something astonishing began. The coalescing of ganglia into centralized control. The first brain, still simple, still small, but enough to start building an internal model of the world. Now imagine the first creatures to see not just light, but shapes, depth, movement. The sea squirt larva, which has a notochord and a primitive brain, swims about in its youth an explorer. Once it attaches to a rock in adulthood, it digests its own brain, never needing it again. A cruel metaphor for stagnation, but a beautiful window into evolution's logic. If a brain is useful, it is preserved and elaborated. Somewhere along this line, behavior became prediction, prediction became learning, learning became memory, and with memory came time. The moment a creature can remember the past and anticipate the future, it exists across time. It carries itself forward. It has a thread, a story, a sense of self not fully formed, but flickering. It is here, in this strange twilight between instinct and reflection, that consciousness begins to breathe. By at the time vertebrates arose fish with backbones. Amphibians that crawled from the sea brains had expanded enormously. The cerebral cortex, in particular, began to evolve in mammals. The neocortex, in humans, would become the seat of language, planning, empathy. But even in early mammals, there was dreaming, learning from experiences, caring for young, feeling fear not just in the moment, but in anticipation, grieving losses, navigating social hierarchies. Each layer of the brain, reptilian, limbic, cortical, did not erase the others. They stacked, they intertwined, and in that intertwining emerged the strange theater of the mind. Now imagine a single creature, a primate, perhaps sitting beneath a tree, gazing at the moon. That primate has just discovered fire. She is warm, fed, and unafraid, and for a fleeting moment, she is not thinking about food or predators or mates. She is watching the sky, wondering, not solving a problem, but pondering it. She is the result of 4 billion years of silent evolution, and in her brain, something lights up that had never existed before on this earth. Self-awareness. She is aware that she is aware. It is not magic. It is not divine spark. It is emergence built atop layers and layers of complexity. Her ancestors never needed to know they were alive. They only needed to live. But she knows. And from that knowledge, all things will come: art, language, philosophy, sorrow, ecstasy. But still, beneath all that, the ocean remains. The deep ocean of the subconscious, the evolutionary inheritance of feelings, instincts, drives. Consciousness is just a thin raft, adrift on that sea. Now pause, drift, let this idea settle. Everything we are our thoughts. Dreams, relationships, identities, they all rest on a physical structure. The brain, shaped by millions of years of survival. But from that structure, something non-physical emerges. Awareness. And that awareness doesn't reside in a single place. It isn't found in a single neuron or circuit. It emerges from patterns, like a melody emerging from a symphony, like color from light. So, what are we really? We are not just flesh, nor just thought. We are the process. We are what happens when the universe reflects upon itself, when carbon, hydrogen, oxygen, and nitrogen, arranged just so, suddenly ask, why? Our atoms are borrowed from stars, our thoughts are borrowed from evolution, and our awareness, perhaps that too, is borrowed. A fleeting window, a ripple, And one day that ripple will fade, but before it does, it will have wondered, it will have dreamed, it will have imagined worlds, built civilizations, sung lullabies, cried under the stars, and in those moments, consciousness will have meant something. So now, as you lie there, drifting between wakefulness and sleep, you are carrying the entire arc of Earth's story within you, from dust to molecule, from cell to mind, from instinct to meaning. You are not separate from the story. You are the latest chapter, a chapter still being written. Close your eyes. Listen to the silence behind your thoughts. That is where life began, and that is where it continues, dotting every breath dot, in every dream dot, in every fleeting, precious flicker of awareness. Sleep now, child of Earth. You are the question and the answer. You always have been. And so, we reach the end of this ancient trail, a story not etched in ink, but whispered in stone, in fossil imprints, in glimmering amino acids, in silent oceans that once stirred with the first breath of life, from molecules drifting aimlessly in warm primordial pores, to minds capable of pondering the mystery of their own origin. The journey of life is not merely scientific, it is profoundly poetic. We are stardust arranged with purpose, chaos sculpted into complexity, a fleeting shimmer of awareness in a vast and patient universe. And though many questions remain, and countless more await beyond the stars and beneath the sea, for now we rest in awe, beneath the same sky that once cradled our first spark. Good night, traveller, and may your dreams drift through the tides of time,